Today we're in Stockholm in the Nordic Institute for Theoretical Physics, NORDITA, and the local organizers here are Evan Gale, Germain Tobar, and Vasileios. So without further ado, I'll give it to Germain, and he'll give some initial speech.
Yep. So first of all, I'd like to thank Tails very much for all your effort in helping to organize the whole circuit, and also helping to organize this local conference, in particular the live stream and smoothing everything out. So today we're going to break up the day into 3 main sessions, so separated by 2 fika breaks, and there's no particular structure to the topics presented, but yeah. So then I'd like to thank all the speakers for submitting an abstract and everyone else for coming along. And so without further ado, I will invite Fabio Costa up to give the first talk. So Fabio is an expert in quantum causality and the process matrix formalism. So today he's going to be talking about one of his recent works on background independence and quantum causal structure. Thank you.
Okay, thank you, Germain. And thank you, Evans and Vasileios. And of course, thank you, Rick, for putting together and pushing forward the quantum circuits. I hope this thing is attached properly. Yes, so it's a pleasure to open this nice event that has been going around the world and recently Europe. So today I'm going to talk about some results from last year. So my talk is mostly based on this paper that was the core of the master student of Lachlan Parker at the University of Queensland. Maybe I will give my personal perspective. But so, yes, background independence and quantum causal structure. So what am I talking about? The setting here is coming from considerations about combining quantum theory and gravity. As we know, it's one of the outstanding problems in theoretical physics to have a fully working theoretical background and predictive background framework for quantum gravity. But there are some conceptual issues that underlie some of the technical issues, and there are 2 that I would like to focus on in particular. The first concerns causal structure. So if you think about the theory of general relativity, it has a dynamical causal structure in the sense that space-time, and in particular causal relations, are not fixed a priori, but can depend on the mass and energy content of your system. On the other hand, quantum theory has the property of having indefinite properties. Mass and energy can have not well-defined classical values, can be in superposition, and so it's expected when you put the 2 things together, some kind of indefinite causal structure should emerge. The second issue is background independence. This is a more standard, more typical topic discussed in the foundations of quantum gravity. And the idea is that general relativity is a background independent theory, so it's formulated without a reference to a particular coordinate system or to a particular background. And it's in principle unclear, or there are some issues in incorporating that into quantum theory. So regarding the first topic about quantum causal structure, in the last years, there has been quite some work in a general abstract framework for quantum causal structures in what is now called the process matrix formalism. So this is a relatively abstract framework, but it is intended to be operational in the sense it should be able to give physical predictions for general physical theories with the indefinite causal structure. So this means in this framework you can talk about Alice and Bob as performing some experiments, and you don't know in advance if Alice is sending a signal to Bob or Bob to Alice, or maybe in some indefinite causal order. And in principle, you can make physical predictions within this framework. However, the way this framework, and I will quickly review how this works. However, this framework is typically formulated in terms of labeled event. So we have some label A that corresponds to an operation A or an observable A that could be performed, and some label B, and so on. And so the assumption here is that you have some reference system that allows you to say what is A and what is B. So in this sense, this is a background-dependent theory. It's a background-dependent framework. And so the basic question is, can we make this background-independent? Can we talk about quantum causal structures without a direct reference to these background labels? How is it going to work? And that's the topic of this talk. Now, just to say, this is a forced exploration in this topic. It's certainly not the full story. But yeah, let's see what we can get from it. So first of all, let us review what does it mean that general relativity is background independent. So the starting point is the idea of space-time. Space-time is defined as a manifold, which essentially it means it's a set of points. So each point, ideally, you imagine it corresponds to a point of space and time. However, you can consider a relabeling of these points. If I say this is 1 o'clock in Stockholm, it means I have a physical reference system that says it's 1 a.m. Stockholm. But if Stockholm and 1 a.m. are all part of my description, I should be able to relabel arbitrarily my points without changing the theory. So a diffeomorphism is defined as a smooth and invertible relabeling of my space-time points. And there are at least two senses in which general relativity is invariant under diffeomorphism. The first is that the field equations, which are the Einstein equations, are invariant under general diffeomorphism. But then there is, in fact, a stronger, and perhaps not universally accepted, but I will say accepted in the mainstream interpretation, there is a stronger point that all meaningful observables are invariant. So it means it's not like you have a theory that has a physical symmetry, that the laws look the same in different reference frame. It means that really all configurations that are equivalent up to diffeomorphism should be considered as actually the same physical configuration. So this is the situation in general relativity. And now I'm going to construct a toy model to make things work and to fit things with this process matrix framework I discussed about. So in this toy model, instead of having a continuous manifold, we consider a finite set of points that are A, B, and C that we label, and these labels A, B, and C we can think of as our coordinates. And each point represents a point in space and time. And then we assume that at each point I can potentially perform some observations, some measurement, or some possible operations. So this is similar to general relativity. Each point has an operational meaning. There could be a system, and something can happen at that point. And in quantum theory, this means we can imagine that there are operations that potentially are performed at each point. So at each point of this discrete space and time, I could imagine performing an operation that gives me some measurement outcome. And these are what we call quantum events. And now very, very brief review of what is the theory of quantum events or quantum operations. So an event most generally, or an operation, is described by thinking about two Hilbert spaces that represent the physical system just before and just after the operation. That can be a measurement or any operation. We have a label A that tells me what is the measurement outcome. So if you're making a projection measurement that can have two possibilities, 0 and 1, then A can take value 0 and 1. And these are completely positive maps, which is just the technical definition. But the interesting thing is that there is a powerful isomorphism that is called the Choi isomorphism that allows us to represent these operations as an operator on the tensor product. So this is a core step in the framework, because now each event is associated to tensor product of two spaces, which is the space just before and just after our operation. OK, and so based on this definition of events, we define what we call the process matrix framework, which is essentially based on writing out this Born rule, which is a joint probability to observe a bunch of measurement outcomes A, B, and C, and so on in all possible points of space-time. And the rule is pretty familiar. It looks like this. And so what appears here are these Choi operators of all the operations events multiplied by an operator W, which we call the process matrix, that lives on the tensor product of all the spaces, input and output spaces for all the events. So this is an operator that is positive semi-definite and satisfies other relations, other properties for normalization. And just to point out that this type of formula has been derived many, many times. Our particular framework is to have a formula of this type without assuming a background causal structure, but a formula like this where you can treat space-like and time-like events on the same footing. Is let's say very popular in the literature. Now, just very briefly, what is this W? This process matrix is the core object of the formalism. So to interpret it, let's interpret this formula again. So we have these MA and MB. So these are what I was saying that operators representing our operations or measurements. And so they play a similar role in this theory as observables in standard quantum theory. And in this sense, W plays the same role as a state. Now, the really key point is that for each space-time event, we have these two Hilbert spaces. So in ordinary quantum theory, a state is understood as something at a given time, while here our process lives on a tensor product of Hilbert spaces for each time. So if I have a single qubit and I measure it 3 times, then you have the tensor product of 3 spaces. Each space is 2 qubits, 1 input and 1 output. So you can think of this process as a state over space-time, with some additional constraints that we will not really discuss. These are more technical details for the purpose of this talk. And just to give some examples, in particular, to give you some examples of particular cases of this process, if these are space-like, let me check. If these are space-like, if you have 2 space-like events, then your process is just an ordinary state on the inputs and identity on the output. If you have time-like events, then you see that you have an operator that connects the output of an event to the input of the other event. And more generally, an interesting thing that comes out from this framework is that you can define processes with what we call an indefinite causal order. And one popular example is the quantum switch. So these are processes that you cannot understand in terms of events localized in space-time. So you have event A and event B, but it's neither A before B nor B before A. And it's not even a probabilistic mixture. So the particular example is one where you imagine that you have a control system, and depending on the control, the operation A happens before the operation B, or for the other value of the control is B before A. So yeah, this is just to give a very, very quick overview about this framework. OK, so this is a sort of the standard framework, and the way it is usually used is, as I said, with the labeled events. So this is usually meant to describe some kind of laboratory setting or some particular experimental situation where we just choose some event A, some event B. But now we want to apply this type of model to what I call this toy model for space-time, where each event is really the most fundamental points of our space-time model. And now, as I mentioned, the fact that we have this label A, B, and C is equivalent to assigning coordinates to the space-time events. And so as I described it so far, this is a background-dependent theory. So to understand how to go to a background-independent formulation, we have to understand what happens to diffeomorphisms. And now, because we have a discrete set of points, our relabelings are simply permutations. So of course, the continuity and differentiability part doesn't play a role here. So it's just when we send A to C and C to B and B to A, something of this type. This is what we call a change of a coordinate system, or the analog of a diffeomorphism. So in short, permutations can be understood as discrete diffeomorphisms. OK, and so from here on, it's almost an exercise. Well, not exactly, but so what we want to do is to define a theory that is independent after permutations, which are these discrete relabelings. And so just to add a little bit of notation, so what happens so our theory is defined by operators on this joint Hilbert space for all events. And so the action of permutation is what you should expect. If you have rho on a system A and sigma event B, if you swap them, you put sigma on A and rho on B. So this is the obvious way permutations act on tensor products. For the purpose of this talk, I'm going to assume that all dimensions are equal, but this can actually be generalized. This is not even in the paper. It's only in the thesis of Lachlan-Parker. And we simplify a little bit of the notation. We don't write tensor products explicitly. So, OK, what does it mean that our theory is background independent? It means that our probabilities are invariant under permutation. So the probability of obtaining outcome A at point A, outcome B at point B, outcome C at point C should be the same as obtaining outcome C at point A at point B, outcome B at point C, and so on. And so, well, at this point, this is the point where maybe this is a little of an experiment, how this is going to work, in the sense that we are going to impose this invariance using the standard tools from what is called the theory of quantum reference frames. So this is the theory that tells us how to describe something independent of a background reference frame. So our reference frame is the label reference frame in this case. And so the relevant group is the group of permutation that defines transformation according to this reference frame. And there are essentially 3 equivalent ways we can model invariant probabilities. And they're all based on this object which is called the twirl, which is taking any operator and is summing it over all the group elements. So in particular, you take any operator on this tensor product and you sum all possible permutations so that you get an invariant operator. And so there are these 3 ways. One, you keep a non-invariant process, but you make the operations invariant. And you can give some interpretation. So there is you can interpret this formula as saying there is a background. It's given by this WAB. But we can only access permutation invariant operations. Another way you can keep your operations non-invariant, and you can symmetrize the process. So you can say that in this case, I do have access to the points A and B. I can make operations that distinguish these points, but my background process is invariant. Or you can make everything invariant, and all these 3 formulas give you exactly the same type of predictions. But this last one is suggestive that you don't have any access to a background reference frame, and the process itself is invariant. So that's the most, let's say, invariant looking formula of all the 3. And maybe one thing to note is that the notion of definite causal order or fixed causal order, the notion of fixed causal order disappears in this case because yeah, we are twirling A before B and B before A, so it cannot be a fixed causal order. And so just to very briefly mention, I'm going to finish in a minute. One of the obvious things we would like to know is how do we reintroduce ordinary predictions? Because at the end of the day, most physical scenarios require making prediction relative to some reference frame. And so this we can do again using relatively standard tools from the theory of quantum reference frame. Essentially, it means we can introduce for each local event an extra system, which is our reference system. And so when we say we make a measurement to point A, what it means is that we measure our system and our reference system. And if the reference gives out the outcome A, that's what defines point A. And so in this case, you can go from the invariant picture to the non-invariant picture in a standard way. And there are some interesting results. I will not spend so much time. Typically, when you have invariance, you have some associated charges. So you can, there is a general theorem that if W is invariant under these group actions, you can sum it as a mixture of irreducible representations. And usually this is interpreted as some kind of super selection rule where you say, well, there is some quantities that cannot be superposed essentially. And so our process can have only this quantity as being type 1, type 2, or type 3. And there is an interesting result that, in fact, these are kind of genuine mixture in the sense if you have W that is a valid processes, these component Ws might not be valid processes for each particular charge. And maybe the very last thing is what I discussed so far is really what we should call classical permutations. And so to think of it in a slightly different perspective, or a classical reference frame transformation, this is like saying if I have 2 objects that are at distance d, it's exactly the same configuration as I move everything by a fixed distance. So this is a particular type of diffeomorphism. But then probably our theory should go a step beyond and say that include quantum reference frame transformation that says a distance, an object 1 at the distance d from object 2 should be the same as having a superposition of 2 objects at that particular distance but displaced by a certain amount. So this type of transformation will not be included in our work, and it's work in progress to see how to include this most general structure. And I'll put up some conclusions, and if there are any questions, I'm happy to take them.
Thank you, Fabio. So does anyone have any questions?
A question about the twirl formula that you wrote down.
Yeah.
Could you also apply the twirl to the product of the two things? And is that different or equivalent to one of the other three?
Yes, so if you mean to apply the twirl directly to the to one twirl to the whole thing inside, the trace formula, that's not going to work because you see that the twirl is a unitary to the left and a unitary to the right. And so if you put it in the trace, just the unitaries disappear, and then this twirl doesn't do anything. So actually, that's an interesting thing because doing that is essentially just a change of basis. So you can say another way. You can say I can change operations and processes, the basis for both, and then I get exactly the same formula. But that doesn't give me an invariant probability. That just gives me different ways of writing the same non-invariant probability. It's an interesting point. This was some confusion from some referees, if I can add. Yes?
So is there an implicit assumption here about the indistinguishability of the events?
There is the assumption that in the theory, relative to, so in the gauge broken theory, if you want, or the theory relative to background reference frame, the events are distinguishable. And they're distinguishable in the sense of, as in ordinary quantum field theory, if you have a region A and a disjoint region B, these represent distinguishable degrees of freedom, regardless of underlying statistic, boson, fermion, or whatnot. When you go to a background independent theory, then essentially the meaning of events, so the individual events lose meaning. So it's not even that there are indistinguishable events. You don't have a direct interpretation of the theory in terms of events. And this interpretation only reemerges if you include this physical reference frame that allows you to distinguish events, essentially. So yeah, in the final theory, essentially distinguishability of events is recovered through a physical system and is not assumed in advance.
Just one small question. So I know this is all finite dimensional, so tensor products are okay, but is it natural to formulate it as in the commuting frameworks?
You mean algebraic quantum field theory?
Even not quantum field theory, I mean just in the language of like where instead of doing a partitioning of Hilbert spaces from the start, I just rephrase everything in terms of the fact that MA and MB are like commuting and whatnot. Or is it not natural here?
It's probably fine. In the way I presented, the tensor product structure is fixed because all we are doing is just making permutations. So there is a preferred tensor product structure assigned to event A, event B, and event C, which is like saying there is a preferred notion of a classical space-time. If you want to include what I was talking at the end, saying at the end, quantum reference frame transformation, that is something that is going to change the tensor product structure. And so in that case, so I think what you say is correct, that you can just rephrase everything in terms of commutation, but I think it's going to be equivalent to the tensor product. But I think the other relevant point is that, yes, in general, one should consider a more general framework where this tensor product structure is not fixed a priori, and you can change it through an appropriate definition of quantum diffeomorphism or quantum permutation, and that's the aspect that is not fully worked out. What does it actually mean to have a quantum coordinate frame? There are many approaches about quantum reference frames, but yeah, there is still work in progress.
Right. Thank you, Fabio. So next up, we have a visiting researcher from the Center for Theoretical Physics at the Polish Academy of Sciences, Jan Clarke. He's going to tell us about his research program in quantum reference frames. So
use this.
Yep. I mean, usually on the back there's an edit thing up the top to make it big. Is it here? So usually, I don't know how you... It's right here.
Okay. First of all, thanks a lot for the invitation. I'm very happy to be able to speak here about my research. This is joint work with Leon Loveridge and Titouan Carrette, and it's work in progress. So the purpose of this talk is primarily to make sense of the title, what I mean by relational, and quantum, and relativistic things, theories. And then towards the end, if I have enough time, I will try to communicate the latest developments. So let me begin with some sort of motivation. So far, well, except the foundational research like the kind was described in the previous talk and this kind of things. Shall I do? Oh, yeah. So we base our fundamental theories on the framework of quantum field theory, usually, and this is not fully satisfactory in my opinion, and I think it is shared in a larger group. So these are some reasons for which this is not, well, good enough, at least in the current form. So far, we don't have any rigorous formalization of interacting quantum field theories. And these are those that we care about in experiments. This framework is tied to the notion of a fixed background spacetime, which doesn't seem compatible with the modern ways of thinking about gravity. And operationality and relationality are, well, in my view, they are compromised in this way of thinking. And I will speak a lot about, well, not a lot, a little bit about what I mean by operationality and relationality as we go. But yeah, okay. So the goal of this research program, the way I see it, is to try to fix this by developing a new kind of framework, like forgetting quantum fields and maybe space-time as well, and try to take the core things from relativity and quantum theory and try to merge them together in a different sort of way. So the goal would be a framework that is operational, which means basically that I want the things that are going to be subject to experiment to be right there in the framework, so that the procedure of deriving predictions from the formalism should be as straightforward as possible. I want it to be rigorous, non-perturbative. I don't want to introduce any sort of background. I want it to be relativistically invariant for compatibility with special relativity. And the way interactions should be implemented in a relational framework, they should always relate to pairs of systems. That's, well, that's my opinion. That's a program I want to pursue. And yeah, I mean, this may sound too much, maybe a bit crazy, but I like to have dreams. And so the purpose of this talk is to show you what kind of progress we've made with these ideas. They obviously related to some other ideas that are around. So I will try to emphasize where we differ from like other approaches to quantum reference frames. And point, well, I want to make the case that this is not something impossible. Okay, so that's the plan. I will first well, provide a perspective on quantum mechanics that is the relevant one for us, aligned with GPT kind of way of thinking. Then I will define what the notion of a quantum reference frame, what does it mean to have a description of a system relative to a frame, then how it is compatible with what we actually, normally how we describe quantum systems without a reference, So we can externalize the quantum reference frames and recover the standard description of physical systems in terms of single Hilbert space, non-relational degrees of freedom. Then the latest development that was done last year and was the subject of my thesis were frame transformations. So we can, after all these things are established, we can consider two frames and we can see how we can describe a system from one perspective and then the other, and we can change between these perspectives. And then at the end, I want to tell a little bit about where this framework can be pushed outside of the quantum theory as we know it. All right. So first, the preliminaries. So the perspective on quantum mechanics is the following. So everything here is infinite dimensional and continuous, which is a distinguishing feature, I think, among similar approaches. So, well, this is basically because I want invariance with respect to the Poincare group, and there are no finite dimensional representations of non-compact groups. So this is supposed to be the basis or a special case of a relational framework. So I need to go there. So states are density operators. Observables are positive operator valued measures. So this is not standard, I think. Well, I think it should, but basically a positive operator valued measure is the most general way to extract the probability distribution out of a quantum state. So it should be thought of as a map that given a state, states are omegas, and this sort of map, I can construct a probability distribution. Sigma is a sample space, F is a collection of subsets, the measurable subsets. So I should be able to construct a measure which is a map that for a given subset of the sample space, which can be thought of as a proposition that I can measure, I can assign a probability. So this is just the Born rule, generalized to this setup. Yeah, so I don't have time to talk about this. This is the starting point, so to say. These are the only things that I'm going to use to build my framework. I don't care about like the actual vectors in the Hilbert space and this sort of things. It is supposed to be aligned with the generalist probabilistic theories sort of way of thinking. Is there a clarification needed here, or we can go? Okay, then we go. Another thing, and this is not non-standard. I want to, well, so for physical reasons that I will advertise, we will encounter the situation that actually not all the operators on a given Hilbert space are available for some reasons. For example, I will require them to be invariant, like we've heard before. I want physical observables to be invariant. And not all of the observables will be invariant. So I have a smaller subset. But then I want my states that cannot be distinguished by the available operators. I want to identify them. So what I do in such a situation, like for whatever reason, I have a constraint on the set of operators that I can apply to my states. Then I redefine my state space by putting an equivalence relation. So these are states again. So I want to identify states that I cannot distinguish. So this sort of quotient space is what we call operational state space because it takes care of the fact that we don't have access to all these things. So this is already a more general thing. So this is a simple procedure. It's very much related to the non-restriction hypothesis that people use. But a striking feature is that it already, I mean, it can be done with preserving all the Banach space structure and all these things. It's a well-behaved procedure, but it brings us already out of ordinary quantum physics because this is not the space of density operators on a Hilbert space. This is something else. And so this is one of the features, not crucial, so if you haven't seen such things, don't worry. So this means that I can span a space of operators out of my given subset, and it has a predual space which is given by the quotient of the trace class. And the only reason I think this is important but not crucial. So, but the point is that in ordinary quantum theory, you have this sort of duality. So the trace class operators in which the states live, they are the predual space to this von Neumann algebra of all bounded operators. And this sort of duality between states and effects is preserved under taking this sort of quotients. which I think is nice, and it makes it compatible also with this GPT kind of thinking. All right, so that's a technical starting point. And now let's think about physics. So the intuition is that coordinates that we use in physics, they are abstractions of physical systems. And it seems that this was at least one of the ways that Einstein thought about this. So he kept talking about these frames and these rods and clocks with respect to which physical quantities make sense. But so the idea here is very simple, but quite radical if you think about it for a bit longer, because so the understanding of what are these classical, the standard coordinate systems, is that you actually have a physical system, but then you assume two things. You treat it as classical, which is no surprise in special relativity, but then you also well, you abstract it out from the description, you idealize it to these sets of coordinates, and this gives rise to the notion of space-time, basically speaking. So the idea is to really go back and not insist on having a background, but only to try to speak about relations between quantum systems, without this picture of embedding them in some sort of background. So that's the intuition behind the reference frames. So, we want to be able to orient them. This is what we do when we apply the Poincare transformation to a reference frame in special relativity. So we want the action of a group on this system, and now it's going to be a quantum system. And we also want some means to be able to describe the orientation. So we also want an observable, a POVM, that's going to measure this orientation. Then we want this relationality principle to be there. So I think it's just a fact of the matter that whenever we measure something, there is some other physical system involved. This is, in a way, is going deeper with the relativity principle. So here the reference frame is being understood as the measuring instrument. So this is the physical thing with respect to which we measure other things. So the observables that are going to be physical, they will be defined on composite systems. They will be gauge invariant, meaning that if I can perform a group transformation, we can think about the Poincare transformation, on both systems, the frame and the system, the observables, they should not depend on this. This we've heard already, a similar thing. And it should also be compatible with the choice of the frame, which I will explain on the next slide. And then on top of this, there is a universality of quantum mechanics. So everything, all the systems are going to be modeled on Hilbert spaces. And this is actually one thing that could be dropped from the framework. So for now, we talk about quantum mechanics and quantum reference frames. But I'm deeply convinced that, this is work in progress, but now I'm really convinced that this can be pushed beyond that in more general probabilistic theories. So here's a definition. A quantum reference frame, it's a quantum system. There is a group, G, acting on all the systems, the same group. And now a reference frame is a Hilbert space with a group action, unitary, weakly continuous, and then this frame observable, so a quantum observable, a POVM, that's going to measure the orientation. And we require this observable to have this covariance property, so that it means that it's, it's just compatible with the group action. So we have a group action on the group itself, and we have group action on the quantum system. And this equation here means that this POVM is going to intertwine the action. So it's compatible. And to really advertise this, I would need to go and give you some examples, but I don't have the time to do this here. So you should maybe for now, just believe me that this is a reasonable thing to do. So and it's also compatible with other definitions of quantum reference frames that people give in terms of coherent state systems. So yes, but let me not go to there. Our definition is the following. A quantum reference frame is a quantum system with an action of a group and a frame observable, which is a covariant POVM. And this is it can be understood as specifying which quantum system is going to be used for your observations and how it's going to be used. What kind of things you will be measuring with this thing. And now I promised to make sense of some sort of relationality. What kind of quantities are relative to other quantities? Well, how to speak about observables on pairs of systems in a meaningful way. So after I've chosen my frame, I restrict the set of available effects that I can evaluate on the frame. So the way to make it formally, make sense of it formally, we can just restrict, we can define such a set and then say that everything is going to be defined with respect, we can do this operational quotienting with respect to this set. But we also want these observables that are physical to be invariant. So this last set here is just means that they have to. We need this invariance on the composite systems. So the this story, the intuition is that the physical things lie in the intersection of these two sets, the physical effects, physical operators. So after I've chosen a frame, I have to take care of this choice. So I cannot now consider operators on the frame that are not my effects, the chosen effects, but I also want the observables to be invariant. And then comes the question if this is possible, because it doesn't seem clear that there are such things. And then comes Leon with his construction. It's the relativization map. So it is a way of generating these things, the observables that are both invariant and framed, so aligned with this choice. So how does it work? For any operator on the system, I can, I need to define what this integral means, but Leon did this. And you can check that it's invariant by just simply changing variables in the integral, if the integral makes sense, but it does. And then it is framed almost by definition, but you can also check and make sure that it's true. So there is a way, and it's called the relativization map, of generating the physical quantities upon the choice of the reference frame that are observables on the composite system, and they satisfy both these principles. So this map is understood as incorporating the actual reference system that normally is being left out of the description into the description. So we define now a relative description to be given on the composite system by this relativized observables. So we understand them as being the physical things, the physically accessible observables. And then we can do the quotienting. So this works on the level of composite system, so I can do this quotient. And also I can represent them equivalently as states on the actual system. But this is maybe I will skip unless you ask me later on. So that's the setup. This is how we think it's reasonable to think about relational quantities. But now I've thrown at you a lot of things that are maybe not fully justified. So what I'm going to do next is try to convince you that this is compatible with physics as we know it. So we can get rid of this reference and recover the usual thing. So now we have this map. It's called the restriction map, which, so for any state of the reference, I have a map from the space of observables of bounded operators on the composite system to the operators on the system. And it is just being done by extending this simple procedure of applying the chosen state on the frame and then leaving the system as it is. And this is understood as conditioning the relative description upon the choice of a reference state. The intuition is that the instruments that we use in labs, they are quantum systems, but they are prepared in states that that make them look classical, and we just get rid of them. And the theorem that is maybe not very difficult, but it's very important, conceptually speaking, is the following. So I take an operator on the system. So this is what I normally have access to in ordinary quantum, non-relational quantum physics. Then I apply the Yen map, the relativization map, and this is the corresponding observable that's relational in our terminology. But then, if I know that my frame has been prepared in a state that's highly localized, then in a limiting sense, I can represent it as the same operator that I would normally care about. Does that make sense? So by externalizing good frames, the frames that admit such sequences of states, I can recover the standard prediction, the standard framework of quantum mechanics. So yeah, under the assumption that the frames that I'm using in the lab have this property, which seems very reasonable, I can go back and do stuff like I normally do. Which means that what we're proposing is not incompatible with well, what we know. So yes, this non-relational framework is recovered in a limiting sense. Okay, now the frame changes, the frame change maps, frame transformations. The setup is the internal frame, so we have a big Hilbert space, and now we decompose it, and two of these systems are going to serve as quantum reference frames. So we have a frame 1 and frame 2. And we've been able to define this transformation that is compatible with having a global state. So this map here to the left, it gives a state that is relative to the first frame, and the map on the right gives a state that's relative to the second frame. And there is a way to map from one thing to the other. And to make it invertible, we need to put another equivalence relation, which basically means that the frame observable of the second frame here has to already be acknowledged by the states in here. This requires much more explanation, I think, but this is how much time I have. So let me just mention some of the directions, and then if you're interested in some specific, well, in one of them more than others, then I can maybe say a little bit in the question part. So I think more general frames and systems can be considered. So we should be able to speak about GPT kind of systems in this language, and also frames. Here, they're the sample spaces of the frames. They're just the group. And I think we should consider also more general sample spaces on which the group acts, maybe transitively. We should be able to speak about interactions between things in the relational way. And I also think it would be very nice to have a categorical implementation of this. So speak about process theories as like symmetric monoidal categories, and define the relational structure on such a thing by mimicking the relativization construction that's here. And all these things, they're work in progress, and this progress is surprisingly fast, I would say. So I'm happy to share these things. Yeah, thank you for your attention.
Does anyone have any questions?
Yeah, thank you, Magdalena. Nice to have you here in Stockholm. I had a quick question just to clarify what you said about recovering quantum mechanics. So I understood that so far this is not a GPT framework, it's Hilbert spaces, and this more maybe generalized notion of the state space. So it wasn't clear to me in which sense one is recovering quantum mechanics rather than, because it seems to me maybe one could interpret just the first scenario as the necessity to include more quantum systems in the description of some scenario versus being able to trace one out without losing a complete description of the remaining one. Is there something missing here?
So when you started, I thought I know what
maybe
to say.
you can answer what you think is the question.
I can say something that I know that seems relevant, maybe. So the thing I skipped was this. So the relative states, the quotient state space is this thing. So we take the states in the composite system, and you identify those that cannot be distinguished by the observables in the image of Yen, which are the relative ones. But then, since this construction is super nice. It's a quantum channel. There is a bijection between states in here and states in the image of the pre-dual map. So the map goes from B of HS to the tensor product, and it has a pre-dual map. So then this thing is inside the states of the system. Can you maybe move a little bit? Yeah, it's here, right? And then we can show that if the frame is localizable, then this set is dense in here. So all the states are relative states, so to say.
I think that actually clarifies my...
Okay, great. I'm happy to talk later if you want. Yes?
Oh, okay. So I just wanted to clarify the first part where you mentioned about restricted observables, right? So if I think, since you already have a Hilbert space here, I can think of it like a representation theory, right? So what's the difference between this restriction with the notion of quasi-equivalence of representations?
Quasi-equivalent representations.
Yeah, if I have one big Hilbert space and I have two representations that fit into the same Hilbert space, right?
So you have a tensor product of representations, or
no?
No.
I'm just saying that if I have an algebra of observables and then I take two representations with respect to, I don't know, the GNS construction and whatnot, and then if two states are quasi-equivalent, that means I can find some representations that agree in this sense. So
maybe, but this is much more general. So maybe in the case, I'm not sure if I fully understand the setup that you want to discuss, but this is any set. It doesn't require even representation of a group. So it's just a procedure that I specify the set of effects and I identify states. And well, I can do it for, like, I can say I identify two states if they can be, if I have a group action and I can translate one to the other. Is this something that you're referring to or not?
Okay, maybe it's slightly different, but I guess maybe it's a technical thing that I shouldn't get this answer right now. Okay.
Yeah, sorry. I'm interested in understanding your question better, but maybe later on.
Maybe later.
Yeah, thank you.
Yeah, my question was about, so this is all phrased in terms of states and effects, but there is no mention of of dynamics and state transformation, let's say when you make a measurement about state update. Is that what you meant by incorporating this into a process theory? So if you want to also include, say, not just the measurement, but how the measurement updates the system, and most generally operation and transformation, is that what you have in mind, to use some process theory for that?
So I think I had in mind something else, a little bit, but let me show you this. These are some things. Okay, so what I had in mind is to phrase this relativization thing as a functor. So I can consider the category of frames. So frames are these POVMs, and you can consider a category of these things with some obvious type of morphism. And then representations of G, these are the things that you're referring to, I think. So you have representations, and you consider channels between systems. So this is like part of this is my process theory. But then I can consider representations, and I can consider frames, and I can think about this procedure as assigning to a frame and a system as an equivariant description of the both. And the understanding is that, so this is what we normally do, and this is what's the actual physics, because we have to include the frame into the description. And you can go back if you have a good frame. Yes, so I think if you want to think about processes, this is probably the way, because the procedure is functorial. So you can sort of make any process equivariant, which means that it's compatible with the group actions and stuff. But again, I'm not sure if I answered the question. Okay, thank you.
All right, thank you.
Thank you.
Jonsson, who is a research fellow here in Nordica. So we're talking about research on
Oh, sorry.
Stay on this.
Yes, I will. Oh yeah, well I can. I think I can press the button here. This we should. Oh no, that's too bad. Well, you will probably be missing one video, the one video I put in. Well, that's a disappointing thing to start with. First of all, thank you, Evan, Germain, Frick, and Vasileios for putting this together and for inviting me. Thanks you all for coming. When I was invited, we were invited to give a bit of an overview talk of topics we're interested in. So I thought I'd go over these, or pick these 3 papers from this year, because they are related to different aspects or represent the topics that I'm interested in, which would be Gaussian states, their entanglement structure in different contexts, signaling entanglement harvesting with our beloved Unruh-DeWitt detectors in RQI, and also non-perturbative methods for matter-light interactions, but also again for detectors and fields. And so when I prepared this talk and I looked at what I had promised in the abstract, and then I looked at the 20 minutes that I have, I realized, oops, I was maybe promising a little too much. So to not fall into this trap of, talking a lot about the first article and then a little about the second and way too little about the third, I thought I'd go the other way around. I'll start by talking about this third article and say too little about it, and then I will say a little more about the middle one. And finally, I want to focus on this one, which is chain mappings methods for relativistic light-matter interactions, because I hope that there for you, or say you and think of the RQI community, there may be some new ideas or methods we could use in there. So let me start with really just one brief slide on this one, which is to appear next week. Probably a rushed collaborator is hacking this on the archive right now. This is with Igor Pikovski from KTH, Lukas Hackel, and Mario Kibok in Melbourne, and Pavel Hodoletsky in Gdansk. And so what we do here is we look at families of random pure Gaussian states. So we say, well, let's look at the family of all pure Gaussian states, n-mode Gaussian states, which all share a certain set of specified marginal states, and then take a random hair unit measure over those. And that's a cool and interesting family that, we were lucky to have Mario Kibok on board, who knows a lot of random matrix theory. But then our motivation was to, how we got into this were questions about black hole radiation, and we think that maybe there is also a nice intuition building or some lesson to that maybe could contribute there to the big problems there. So stay tuned for that if you're interested next week. And the second paper, and here I will say a little more, is about entanglement harvesting near 3 + 1 dimensional Schwarzschild black holes. That's basically a follow-up to an earlier paper we had with Mark and other students of his, where we looked first at signaling. And it's related to all, the interesting things that happen when you are close to a black hole. And here, and this actually is, this article relates to the title that I put on my talk for numerical methods. Because here, Joao Caribe and Mark Casals did all the hard numerical work that goes into calculating the green function that you need to get to calculate entanglement harvesting and signaling between detectors. And yeah, so here is the video that's missing, so I will try to dance it for you. The question is, what happens close to a black hole? So what was going to be happening here was that you would see a black hole in the middle, and you would see Alice here. And then from Alice there would emanate a light cone, and whereas in space, in flat space-time, this would just spherical ball just expanding. What happens if you have a black hole in the middle is that this ball starts to expand, but then it starts to fold around the black hole, and it starts to see itself again. It intersects with itself. That's where caustics form. And then when it goes the other way around, there's even again a point where you have another meeting point, so again caustics form. And so you get this involved structure of null geodesics sort of winding all around the black hole, opening up for different paths on which information signals can travel from Alice to Bob. And also this is interesting thing of when you do this, that every time the light cone goes through caustic, the singularity structure of the Green's function changes, which changes. So, and on changes, and on top of that, you always have the Green's function being supported not only on the light cone, but also inside the light cone. Strong-Huygens principle breaks down. So you also have these tail contributions that you all need to take account. So to sum this up, calculating the Green function gets really complicated, and that is nevertheless what Mark and Joao were able to do. And I'll just quickly give you an overview of what we did. We considered the Bulba, Hartle-Hawking, and Unruh states. They really all behave very similar for the questions that we looked at. Only some minor differences due to the expected differences in the different noise the single detector sees in these states. And what we found is that this gravitational lensing of the light cone close to black holes really allows for entanglement harvesting to appear there again. Now, why would that be maybe surprising at all? I picked this one figure to illustrate it. So again, we have Alice sitting here close to the black hole. I think it's 6m, radius 6m, and then a bunch of bobs sitting around at different angles, also at the same radius. And if we pick a bob that sits close, then what do we see here? Well, after some propagation time, a strong signal comes in. These blue lines measure the correlations between the two detectors. So we see the correlations overcome the background noise, and what this means for you as an easy takeaways, here the detectors can get entangled due to the interaction with the field. Now if you move Bob further away, then he may still be able to get a signal and overcome the noise, but here there's somehow a darker shadow corner, say 3/4 pi. There is some signal coming in after a time, but it doesn't overcome any longer the local noise. So these two detectors, when you couple them and decouple them again, they would be in a separable state, not entangled. And now, in Minkowski spacetime, of course, if you're at that point and then you move the detectors even further apart, well, we get less and less of a stronger signal. Not so here. If you go to the antipodal point, you see that there where these caustics form and suddenly light rays hit Bob all the way from Alice, the signal again gets pretty strong. So you see, well, again, these two detectors can be entangled. And if you're like to the connoisseurs or the experts in the audience, what we also found is that there are both regions where, well, most of this entanglement should be associated to the communication or signaling, but also shortly after the caustic you find setups where really you can tell that this entanglement is extracted from the field. It's pre-existing vacuum entanglement that is swapped out of the field and onto the detectors. All of that to be found in that paper. And now the thing that I want to focus on most today is this work from the summer with Johannes, who's we were colleagues at Munich. Yeah, there it is. And now he is at the ETH in Zurich. And here we used chain mapping methods. We had also another project where we used them to look non-perturbatively at strong interactions, or ultra-strong interactions for so-called giant atoms. That's a quantum optical setup. And this one would be the other where we applied this to relativistic fields. Wanted to check out what we would be able to achieve there. And we picked as a demonstration for this Unruh radiations, the question, okay, what radiation is emitted from a uniformly accelerated emitter atom or particle detector? So the takeaway I hope for you would be that, well, maybe, but both conceptually see what these chain transformations actually are, because they, I think, are already interesting when you, just conceptually when you're thinking about matter-light interaction, but then also to see what numerically you can achieve with them. So what are these starter chain transformations? Well, the idea is to cast an interaction between which looks like a star. So we have a system, in our case the detector, which couples linear to a bath, to rewrite it exactly in a form that it takes this shape of a chain. Because in this shape, it's very amenable or very well suited to apply DMRG, matrix product state methods to it. Full stop. And so these transformations are widely known and widely used, in particular for open quantum systems. And depending on the community, they will go by different names. You can look for Cholesky transformations, T-DOPA, reaction coordinate mapping. And typically, what is done is that people are most interested on observables in the system, not so much about what the bath does or observables on there. But that's what we wanted to get at. We wanted to keep track of the bath and in particular evaluate radiation that is an observable on the bath and see what we could achieve there. Now I said linear interaction. What do I mean by that? I mean that the interaction Hamiltonian between the system, here we have our sigma x operator, but that doesn't really matter, can be any operator here, that the interaction between system and bath is given by a simple tensor product, where here on the field, the bath, the waveguide side, you have an observable which is linear in creation and annihilation operators. Right, so that's why this is a star shape. We have the system talking individually to each of the eigenmodes of the field, which is a bath of harmonic oscillators. Now what I can do is I can take all these modes together, right? I can take this term here and take it to define a new mode. Let's call it C0. And I have to normalize it properly, but what it does is it recasts our interaction Hamiltonian into our system with a slightly different coupling now, but talking to only one mode of the field. If I now go on, I look at, okay, what does this mode couple to in the other than the system in the field, and then what does this mode couple to, and so on. So I apply this Cholesky transformation, tridiagonalization really of the Hamiltonian matrix. This is what I end up with. We have the system talking through the old interaction Hamiltonian, but now to only one mode. And in here we have hopping terms only. And what is important is that these modes here, the chain modes, share the same vacuum as the initial modes. The Bogoliubov transformation between them is non-mixing, so particle preserving. And this transformation is exact. If you have n modes here, you end up with n modes on the chain. If you have infinitely here or a continuous path, you end up with infinitely many modes here, typically. Which is great, and at that point you can work conceptually. If you want to put it on a computer, of course, you can only treat finitely many modes. So you have to truncate the chain, and that introduces some errors. But you can well control them. In particular, if you start out in the vacuum and you do some excitation here, you can be sure that as long as this excitation hasn't reached down and maybe reflected back into your system, that you're actually treating the full exact system. You haven't introduced any UV cutoff or other cutoffs that may introduce causal problems, causality problems, which we're usually fighting with when we want to look at a relativistic scenario fully. So that's what I found very appealing about these. Depending on the numeric methods that you use, more problems may come in. I mean, when we put in harmonic oscillator here, of course, we treated this whole thing just with Gaussian methods, and they can be very precise numerically. When you do MPS, I also will show you more problems show up because, I mean, just as numerical errors from your method. Now here I pointed out this works for the vacuum. What do we do? I mean, I mentioned Unruh effect. What do we do for thermal states? Well, even there you can do something. See if your system couples to a bunch of states, which here are in a thermal state. That's what we indicate with this red one. We can play the thermodouble field state trick. We can add a negative energy copy of our system. So to each of the eigenmodes here, I now just add another mode. It has the inverted frequency. And I choose the joint state of these mode pairs such that they are in a two-mode squeezed states, so pure state, each of these pairs. But if I take only one, then this is in a thermal state. And now I can take each of these two modes, I can unsqueeze them, so to speak, and then I end up with now my system talking to, well, twice as many modes, but all of them being in the vacuum in the ground state. And from here then, and under this transformation, the Hamiltonian doesn't change shape. And at this point, we are back in the old game. We can now do a chain transformation and again run the same kind of methods here. So what then did we find, or how did we apply this to the Unruh effect? Maybe this, if you know the Unruh effect already, sort of looked familiar to you, and that intuition is exactly right, because in the Unruh effect, the role of these modes is basically played by the Rindler modes and the Unruh modes. So what did we do here to model this thing? We were interested in the radiation that a particle detector that we drag along the uniformly accelerated world line would emit into the field. So our interaction Hamiltonian now looks like this. This is the, well, basically, if it's a two-level system, that's the Pauli X operator. If it's a harmonic oscillator, then that would be one of the quadratures, Q, say. And we coupled it to the field at, oh, this should be in convention pi, because it's the field, the momentum of a massless scalar field in 1 + 1 Minkowski space. And we smear this function out, we smear this coupling out by a Lorentzian. Now for the experts, why did I use a Lorentzian? We have that point in the paper. At some point, certain integrals were just solvable for the Lorentzian in the thermal case, or there was no solution known for the Gaussian, which would of course be nicer to use in the first place. So, but to make this work, a Lorentzian there. And right, then if you then put this model basically into Rindler coordinates, you drag it along this world line here, then you see that naturally your detector here comes to Rindler modes, so that's where we started from, made this transformation, oh great, and did chain simulations. So what did we find there? Well, I mean, this is just a picture to show that we did it for us to look at jointly, but maybe to give you some details on how far we could go with this. What you see here is plots for harmonic oscillator emitters and for two-level systems, either starting in the ground state or in the excited or one-particle state of the detector, and the radiation profile that was emitted to the left and to the right from this detector. So you see, for example, this bump here is when we switch off the detector. Of course, we sort of rip it out of the field. That leaves energy density behind in the field. And the other bump here, that's from switching on the detector. But here in the middle, we have oscillatory features that are somewhere from in the middle. Acceleration here wasn't very strong. L times the acceleration of the detector is, as the length scale of the Lorentzian is just 1/10. And how long did we calculate this for? Well, we started them off at proper time minus 7L. And here we were limited by the length of the chain. We used 250 chain modes for this. And so we analyzed that, well, after 7L simulation time, our excitations hit the end and reflected back, so we wanted to end there. And another model is another limit of this model is, of course, that this product can never be too large, otherwise you're really unrealistically smearing out the detector way too far into acceleration regions of very high acceleration. Here in a log plot, now only the harmonic oscillator for higher and higher oscillations. You see there accelerations, you see they're rather regular. You also have a nice symmetry between left and right moving radiation, and in fact you can show that this has to be that way. And what we found now, whereas these are evaluated directly from the as rather complicated observables from these chain that we obtained when we started with the thermal state, we found that at these lower accelerations still, you can really understand this emitted energy density profile by looking at what a detector at rest would emit and Lorentz boosted correctly. So from the relativistic side, that maybe is a little boring because really nothing very unexpected happened there. On the other hand, if you look at the method, it's quite, assuring to see that these very different calculations to very high precision coincided here. These things here, highly frequent oscillatory patterns, they point towards the problems. These seem to be error signatures. We have a longer discussion in the paper of what happens when your excitations hit the end. Thank you. Hit the end of the chain. So that's one problem. And how soon your observables are dependent on such errors depends, of course, where on the chain they live. If you think of system observables, you have much longer simulation time before they get affected. If you you look at the energy density, you need to be very careful very soon. So depending on what observable you look at, you may be able to derive observable dependent error bounds. That would be an open question. And then I mentioned that matrix peroxide methods can be sensitive earlier, and to illustrate that, they, for example, have to look at what time step in your, what time trotter step in your discretized time evolution is the optimal one to use. So to illustrate this is a case where we have free field, so this energy density should propagate undisturbed from the left to the right. This sort of worked, or this worked for time steps 10 to the minus 3L. If you go for longer time steps, you see that there is a large deformation kicking in very few. But shorter time steps aren't always better, and we can explain why. It's like a Zeno-like effect. You see that here, even after some time steps have, like early on, there are bad perturbations or error terms appearing in these energy densities. So here there's an extra, you need to worry much more about your numerical parameters in this case. So this certainly goes into the outlook on what's left to be done. What would be very cool now, I think, would be to look at 2 and more emitters. Again, maybe do entanglement harvesting and communication scenarios with this. And there's also some math work left to be done. Not so much maybe when you start out with a discretized bath, but when you do it for continuous baths. So 1 emitter, you can directly connect to the theory of orthogonal polynomials. For 2 emitters, it will work, but mathematically I think it's interesting to work that out. I mentioned the error bounds for bath observables, and then of course what's left to be done is compare this to other alternatives. Quantum optics has many more approaches and methods to offer. And also, for example, this question of the Unruh radiation has of course been treated in certain approach or works, also analytically non-perturbative already. So there's a lot to benchmark against there. So with that, thank you for your attention, and here an overview of all the works I tried to make you interested in.
Thank you, Robert. So now, do we have any questions?
I just have 2 short ones. So one is that higher dimensions, there's no DMRG, right? Or at least there's no equivalent of DMRG that works.
No, that works. I mean, this is we here use 1 + 1 dimension, but this carries through for any dimension. It really only depends on your coupling here being linear, and that applies also for higher dimensions. The point is, I mean, this can be in higher dimensions, but the chain you get is 1-dimensional if you have 1 emitter.
Okay. And the second thing is that, do you know if anything that, so this is kind of like from open quantum system kind of tricks, right? But there's another thing that people like to do, which is the Polaron transformation. Do you know if there's something you can do here?
This got us started to read up on the Polaron transformation, but
basically you reshuffle strong coupling with the detector into the bath so that the detector now couples weakly to the rest that has got reshuffled. Yeah, I mean, Polaron transformation would be like an expansion from 1 over lambda, right? I mean, come from strong coupling and going in there. So we have actually had some discussion. I mean, I'm aware of this. I mean, but Polaron is still an approximation, right? Or I mean, perturbative. Or the nice thing about this, I find, is exact and also numerical methods. Yeah. So that's then. But I mean, yes, Polaron transformation I see is one of the points of alternatives to compare with. Yeah, absolutely. In particular, if you're interested in actual results for a certain setting, you should look with what method you go the furthest in your regime of coupling strength or point of interest. Yes.
Right. If there are no more questions, thank you.
Thanks.
Right. So next up we have Evan Gale. So next up we have Evan, who's a PhD student under the supervision of Magdalena Zych, and he's going to be talking about the localization problem.
Excellent. Thank you, Germain. So I'm Evan. I'm a student of Magdalena's, actually based in the University of Queensland. I'm just here visiting. I'm here to talk about the localization problem in the Unruh-DeWitt model. This is based on a paper I published earlier this year, along with Magdalena. You can find it in Physical Review Dane. So to start off with, we'll start very broad. So in relativistic quantum physics, it has its origins in the 1900s. It started with Einstein developing special relativity and quantum theory. In the 1920s, we developed relativistic quantum field theory, but we still have a bunch of open questions in the context of relativistic quantum mechanics, namely, how do we define a particle in quantum theory? Can we provide a consistent single particle description of relativistic quantum mechanics? And what does the transition from relativistic quantum field theory to non-relativistic quantum mechanics tell us? This last question is particularly helpful in looking at quantum gravity and aspects there. To explore some of these questions, we look at the Unruh-DeWitt detector model. This was originally proposed by Unruh and then simplified to a monopole type system by DeWitt. The basic idea is that we have some two-level system, like an atom or what we call a detector, which we couple to a quantized scalar field. Usually it's a scalar field. The interaction Hamiltonian takes the following form, which features this monopole operator, or also called the polarization operator for those coming from atom-light interactions in atom optics. The basic idea there is that we can change the energy level of our detector in its coupling to the field. The field can be decomposed into a superposition of some mode functions. Here we take the plane wave modes. We are simply working with a Minkowski spacetime. The Unruh-DeWitt detector model has quite a few different applications. It was originally studied in the context of curved spacetimes for quantum field theory, but it has also been applied in the context of relativistic quantum information, particularly looking at entanglement harvesting and such, mainly entanglement type applications. Recently, it has also been used to develop an idealized model of the atom-light interaction. Where have I gone? Okay. We want to extend the model a bit to feature a quantized center of mass, because usually we treat the detector as some point-like model. That can lead to problems that we might want to resolve, that there are a few ways of developing this model a bit further. The first such extension was proposed by Unruh and Wald, where we take a detector localized to some box, and we have some discrete energy levels for a detector, which we can then obtain the following monopole operator as a function of the wave function for the ground and excited state energy levels. Another way, or alternative way, of introducing a quantized center of mass was developed by Strisselberger and Kempf. Here, this is more along the lines of an idealization of the atom-light interaction, and so we do not have any such potential confining our detector. So our detector can delocalize or spread out. We introduce a kinetic term into the detector's free Hamiltonian, where, again, we're assuming some non-relativistic detector, like in the previous Unruh and Wald model. An equivalent model was treated by Wilkins in the context of the atom-light interaction, where the electromagnetic field was employed rather than some scalar field. And so this stuff has been looked at quite recently and gotten quite a bit of interest. But we want to go a bit beyond these two models, because both of them assume this non-relativistic detector. So what we really would like to do is to treat the center of mass relativistically. There are two different ways of doing this. One is through a second quantized model in the framework of relativistic quantum field theory. The other is to try and model our detector in a first quantized way within the framework of relativistic quantum mechanics. We're going to consider both of these models, but let's start with the second quantized one. So in this case here, actually it goes back to Unruh's original paper. Unruh proposed two models for the detector, one being this first quantized box detector model, and the other was this second quantized fully relativistic model. In this case here, the basic idea is we're replacing the ground and excited state levels of our monopole operator with ground and excited state fields, which allow us to model the change in the mass of a detector. The interaction Hamiltonian takes the exact same form, where we have, again, our monopole operator appearing, with the small caveat being that the coupling constant now is distinct from the first quantized coupling constant. They're dimensionally different. I'll speak about that in a bit more detail later. Now, this model was simplified in a quite recent paper by Giacomini and Kempf, where they restricted this model to the one particle sector. So they're restricting the Fock space of the detector. When one does that, then the position and internal degrees of freedom are coupled, and you obtain these position states that appear in the interaction term. Now, this looks very similar to the non-relativistic model that we previously looked at, except that the position states here aren't quite defined as you might expect from non-relativistic quantum mechanics. They feature the Lorentz invariant integration measure appearing here, and as a result, one does not have a Fourier transform of the position states in terms of the momentum eigenstates. So that's actually quite interesting, and it leads actually to a bit of an interesting question here. Before that, there are a few caveats to clarify. So one might actually ask, hang on a second, why do we have two detectors here, psi G and psi E? Well, we only really have one detector, and there's different ways of factorizing the Hilbert space here. In this case, we factorize the Hilbert space to have a ground and excited field, but we can also separate out this internal degrees of freedom, and we only have one center of mass for this detector field. This is really just giving us an effective description of the detector in terms of this composite scalar field. Another caveat is that this detector is not running localized. This is what I sort of mentioned briefly. So in looking at the model developed by Mr. Zellberger and Kempf, no potential is postulated, and so the detector will spread out or delocalize over time. Typically, one wants the detector to remain confined to a finite region. This is why Unruh proposed a box detector model originally. And more recent work has also been developed by Eduardo Martin Martinez and Rick Pierce. In principle, one can synthesize these two different notions of localization by confining potential and localization in terms of a center of mass, although we don't develop that in this talk here. Okay, so I've outlined the second quantized way of treating a detector's localization. We could also approach the localization from the opposite direction, where we take a first quantized model and we attempt to make that more relativistic. The most obvious way of doing that is we choose a frame in which our detector is boosted, and we simply quantize the Hamiltonian, in this case here putting a hat on the P. We also have to put a hat on the M because our detector is some atom or some two-level system, and we have to describe the change in the energy or mass that results from the state in which it's occupied. A good motivation for this might also be neutrinos, which exist in mass superpositions, and where we would have this sort of possible projective operator on the internal states there. Okay, so the interaction Hamiltonian we expect for our first quantized model will take the same form as it was in the non-relativistic case we expect, where we have some internal degrees of freedom and we have these position degrees of freedom for the center of mass. But we have to be a bit careful about how we're defining a few things. So in particular, what time parameter is our Hamiltonian at generating time translations with respect to? So I've been working in the Schrödinger picture just to avoid any explicit time dependence for the moment. But the simple way is that given that we have an inertial detector, and conventionally when one wishes to speak of the Unruh-DeWitt model, one evolves with respect to the proper time, we can simply take a frame, at least in this inertial system, to coincide with the coordinate time. Our proper time coincides with the coordinate time. That's just by a given time reparameterization. More carefully, we have to actually define what these position states are in this sort of first quantized picture. So we could employ the same localization as we found in the quantum field theoretic model, but it's quite natural to take the Fourier transforms to just be, to take the position states to be Fourier transforms of the momentum eigenstate, in which case it would entirely agree with what we have from non-relativistic quantum mechanics. And the very last point is that, as I mentioned before, the coupling constants between the two different models disagree. So we have to actually find some way of relating the two models in terms of this coupling. What we do is that, or what we expect, is that when the detectors are at rest, the two models should coincide. And so that gives us a constraint on how to compare the two couplings and how to make them dimensionally equivalent, given by this proportional term in terms of the masses of the detector. Okay, so a brief summary is that we have a first quantized model. It's given by this linear combination of the this term here appearing in terms of linear combination of the ground and excited energy levels for our first quantized localization, which is just a Fourier transform. But for the second quantized model, it's exactly the same thing, except that we now have, of course, a different coupling constant, and we have this Lorentz invariant integration measure appearing in our localization. Okay, so we proceed as we do, as per usual, in the Unruh-DeWitt model, which is that we want to look at some particular observables of the system. Here, a small caveat is that we're treating this more as an idealization of the atom-light interaction. And so usually one treats a detector which goes from the ground to the excited state, and we interpret that as a detection of a particle. Here we're treating our detector more as an atom where we take it to be in some excited state initially, and we want to look at the spontaneous emission of our detector to some ground state energy level, which leads to an emission of some field quanta. We work in the interaction picture, so all of the evolution will now be done with respect to the free Hamiltonians. And of course, we look at, we assume weak coupling, and we look at things to first order in perturbation theory. Okay, so of course, we just go through the usual methods. We find the transition amplitudes and probability. And what we really care about here, and usually what's reported, is the transition rate. If you go through all of the calculations, you'll obtain a transition rate given of this form, which is a functional of our detector wave function, convolved with this template function, it's called. This template function is, has units of energy in our definition, and it effectively encodes all of the dynamics from the Hamiltonian for the given system that we want to consider. Okay, so looking at the different first quantized and second quantized template functions, we find actually something that's very interesting, resulting from the two different localization schemes we've prescribed. In the first quantized model, we have a result that's proportional to the relativistic dispersion relation, while in the second quantized model, it's proportional to the reciprocal of this dispersion relation. And just to illustrate that a bit more explicitly, we have this quite different physics going on here, which is very dramatic for large momenta. This can also be compared to the classical case where we're not keeping track of any of center of mass, and so the template function just coincides with the energy gap. To get a few more results, we can also consider a non-relativistic detector and a semi-relativistic detector. This would be equivalent to the previous models I gave at the very start of the talk, where we have just a p squared on 2m for our kinetic term. In this case, we have quite a different behavior for low momenta, even in the regime where we might have interesting effects. The semi-relativistic case is something that I've coined, but basically, when we have two different energy levels for a detector, we have this mass defect corresponding to the splitting of the ground and excited energy levels. If you want to include that in the description of the dynamics, then you get something called this semi-relativistic regime, in contrast to just treating the mass as some C number, which isn't quantized. Okay, and this is, of course, for very small energy gaps. You can also consider it for larger energy gaps. Here again, we have the same behavior for our relativistic models. There's some disagreement here between the classical cases. This just comes from which mass we have chosen to normalize with respect to. So everything is with respect to the ground state mass. We could have also normalized everything with respect to the excited mass, which would likely, we would likely find that these different models would coincide if that were done. Okay. To get a few more explicit results, what I want to do is I want to assume our detector has some Gaussian profile. This can generally be assumed because we can always, for some arbitrary distribution, take a saddle point approximation of our full distribution and obtain some kind of Gaussian approximation. We can actually get analytic results if we assume that our detector is at rest. And in that case, we obtain this Gaussian product with a modified Bessel function of the second kind for the first quantized model. For the second quantized case, we get this hyperconfluent geometric function out. And we can then also plot and see what the different models look like. In this case here, we have the width of our Gaussian to be larger than the Compton wavelength. And we find that the relativistic first and second quantized models agree. They coincide. That's actually perfectly expected because if you remember from the template function I showed before, both of the two models coincide when you're at rest. Quite interestingly though, if we localize below the Compton wavelength, then one does actually get disagreement. Of course, this is a bit suspicious because we can't really localize below the Compton wavelength, unfortunately. When you start doing that, so the usual argument goes, you have enough energy to create particle-antiparticle pairs. And this would destroy any kind of localization that one might want to achieve. So ideally, one would look at this for general momenta or higher momenta. Unfortunately, I've so far been unable to achieve results for that case. One has a very highly oscillatory integral that doesn't even allow for approximation methods like the stationary phase approximation. So I can't obtain explicit results here. But just by looking at the template functions, one knows that when we convolve our probability density function with one of these template functions, we will get very different results. But of course, all of this is heading to a really important question, which is what would one observe if this experiment were performed? Would we expect to see the results of the first quantized model or from the second quantized model? Which of these localizations is actually the correct one? In fact, maybe there's actually something wrong we've done here. Can we even define our relativistic position operator as equivalent to this non-relativistic position operator? Which of these position operators is the correct one? And going back even further, how does one define a relativistic center of mass? So this is maybe getting a bit away from the quantum mechanical side of things, and it is sort of focusing on a particle-based interpretation. You can develop this in a more field-theoretic framework, but historically this was developed with particles in mind. If we have some many particle system, then the way that we define it in non-relativistic center of mass, forget relativity for a second, is it's just the weighted average of the position vectors. And this is some unique definition. Everything gets a lot more complicated when we bring relativity into the picture. Because in fact, there are different ways one could define, or reasonably define, a relativistic center of mass. And this was first investigated by Price. I put an asterisk there on first because no one ever, the person who's claimed to be first is never actually first. And this is same true here. There's people a bit before Price that looked at this, but Price gave out 6 different definitions for a relativistic center of mass. All of these sort of are sort of quite sensible. The first 2 are basically choosing some frame, a Galilean frame or a rest frame, where you, like in the Newtonian definition, weight the position vectors by the rest masses. In definition B, you also then can obtain results by just transforming according to the Lorentz group. Now, there's a few more definitions, of course, that they listed out, but the ones that we actually care about are actually just definitions D and E. So here we define our position vector in the rest frame, weighted by the dynamical mass energies, and we transform according to the Lorentz group. And in that case, we have a Lorentz invariant position operator. We can alternatively define our position operator in coordinates where we have a vanishing Poisson bracket. And in that case, we actually have a result that agrees with the intuition of A and B in that we have things appropriately defined in the rest frame. Okay, so following from this kind of idea, it's going a bit now away from this viewpoint of a many-particle system, though. We want to define how a relativistic position operator should be thought of in terms of quantum mechanics. And Newton and Wigner approached this question by requiring any properly defined position operator satisfy a set of invariance conditions. All these conditions are actually really quite intuitive. So if we have some localized system, then these localized states, taking a superposition of them, should also remain localized. It should be invariant with respect to spatial rotations and reflections. The states should be orthogonal with respect to translated states, which is kind of getting at the idea that we should have a delta function if we take the inner product of these states. And lastly, the generators of the Lorentz group should be applicable to these localized states. If we do all of this, we in fact find that this is equivalent to Price's definition. In fact, sorry, I should say definition E, because there are 6 of them. This is from the fact that we have a vanishing of the commutator, which is a result, I think, mainly of condition C. In the classical limit, this would correspond to the vanishing of the Poisson brackets. And moreover, this also coincides with the non-relativistic position operator. So this is exactly the quote-unquote first quantized position operator that we introduced. And it is, or in other words, the first quantized system, we imposed a Newton-Wigner localization. However, there's different ways of defining a position operator in relativistic quantum mechanics, as we've just seen from the center of mass discussion. So Phillips approaches this from a quite different, well, the exact same approach in terms of defining variance relations, but wants to impose different constraints to define what a position operator is. So in this case, we again have the first 2 conditions as we had before, but we add a different constraint, which is that the localized states have to be invariant with respect to Lorentz boosts. And this condition is actually not compatible with the other conditions that we impose from Newton and Wigner. But to make sure that our position states are uniquely defined, we also have to have a few more properties. So of course, our localized states should be normalizable within some finite region, and our localized states should be irreducible. This definition is exactly equivalent to Price's definition D in terms of this Lorentz invariant localization. And just a small aside, moving more towards a second quantized interpretation or field theoretic interpretation, these Phillips states are equivalent to the action of a field operator on the vacuum. Okay, so we have 2 different localizations. I don't have the time to go into all the details here, but one immediate question that one can ask is, how are these 2 localizations related? And the answer to that is they're related in a very interesting way in that you can map between the 2 and the associated operator representations via something called the Foldy-Voltaisen transformation. And there's been a lot of discussion of this transformation and also of localization more broadly, which says that there's a very close relation between what these 2 definitions of a center of mass sort of describe. Moving away, I guess, from that transformation, and just to focus on localization itself, how should we be interpreting these 2 different things? And the answer is it's a bit unclear. We expect, I guess, intuitively that the more fundamental second quantized model should be correct, but its position operator is not Hermitian. Now, this is maybe looking at things from a more particle-based ontology, which is that starting from what Phillips was thinking about, we have some well-defined particle. We want to define a position for it in a Lorentz invariant way. The operator there is actually non-Hermitian. It's a bit more natural when you look at it in a field theoretic perspective, because, well, it's just going to correspond to the field operator. Meanwhile, the operators in the Newton-Wigner representation agree with what we expect, particularly in the classical and non-relativistic limits. But there's no Lorentz invariance for the localization, and in fact, we have some non-locality issues. So is this Newton-Wigner representation the result of coarse graining, or does it have a more fundamental status? There's some open questions here that we have to ask. But just to quickly summarize, the localization problem in the Unruh-DeWitt model is what we sort of have come across, also for the atom-light interaction, if one treats this as an idealization. There's some surprising disagreement between the first and second quantized models. And in principle, these are experimentally distinguishable if one takes a detector boosted with respect to the lab frame. It leads to the very important and interesting open question, which is, what is a particle? Well, this has already been answered, really. The conventional answer is just a particle is what a particle detector detects. But then we can ask a bit more, what is a particle detector? Well, a particle detector is some localized system from which we can perform local operations on a quantum field. But now we again push it back a bit more and so, okay, well, what is meant by a localized system? For a relativistic particle detector, how should we define its localization? And this is starting to get into answers that I don't have at the moment, but which, of course, we'll hopefully be looking at. Okay, thank you.
Thank you. All right, time for one or two burning questions.
Yeah.
So spontaneous emission from atoms must have been observed by atomic physicists and molecular physicists. And which one of the results correspond to that?
I don't know. I actually haven't looked at those results yet, but I'm not sure. Yes, I assume that the results actually haven't been obtained, but because you have to, I think, move at quite relativistic speeds. But it would be, I guess, looking at more to see if there's any calculation or any data that would, I guess, clarify this already.
So the standard calculation would be with non-relativistic atoms or quantum fields?
Yes. I would also expect, yeah, that most of the experiments that have been done, as in the literature theoretically, they just assume a non-relativistic center of mass. But which is probably why I haven't really seen this much in literature. Yeah.
Okay, thank you. Any other questions will continue over the break. So thank you again.
Hello, welcome back to the second session of the Stockholm RQI Circuit. We have 4 speakers who will be going through what they're talking about. A small comment for speakers who are joining us in person. We have a table here on this side, which is meant to indicate when you're out of the view of the camera. So I recommend staying on this side when you talk. The next speaker we have is Jerzy Paczos, who will be talking about Hawking radiation for detectors in superposition of locations outside a black hole. Take it away.
Okay, so first of all, thanks to the organizers for setting this up. Thank you all for coming to my talk. I'm gonna tell you about the research that I did in collaboration with Luis Cortés Barbado from the University of Vienna. And we were looking at the Hawking radiation phenomenon as perceived by detectors in superposition of locations. So, first of all, Hawking radiation is a proposed thermal blackbody radiation released outside the black hole horizon. This is an effect of quantum nature because, as we know, classically nothing can escape the black hole horizon. And usually when we consider it, we think of a black hole that fixes the background, fixes the metric, some quantum field living in this metric, and a detector interacting with this quantum field, which we can find out that will click from time to time, testifying to the presence of some radiation. This surprising phenomenon is now well established theoretically. It is also deeply understood, which does not stop us from asking more interesting questions. In particular, based on the previous research of Luis and his colleagues, this time we ask what is the shape of the particles emitted by black holes? And what do I mean by that? We know that in quantum mechanics, particles are not well localized objects. Instead, they are rather blurred in space. This means that we can detect a particle by putting a detector here, but we can also shift the detector slightly to the left, slightly to the right, even here, and we can still absorb exactly the same particle. And now the idea of Luis and his collaborators was to put the detector in superposition. They were investigating the Unruh effect, the close relative of Hawking radiation, and they put the detector in a superposition of trajectories and argue that based on the final state of the detector, one can make conclusions about the spatial distribution of the particles. So what we do is we consider a Schwarzschild black hole, so a static, not charged black hole, a massless real scalar field living on the space-time fixed by the black hole, and a particle detector that follows a superposition of static trajectories around this black hole, of classical static trajectories. So more about the details of our problem. We have metric given by the well-known Schwarzschild metric. We have 3 kinds of dynamical degrees of freedom, which are the internal energy levels of the detector, the static trajectories that are followed by the detector, and states of the field. we assume that the interaction between the field and the detector is given by the standard monopole interaction Hamiltonian. So here we have a small coupling constant, a switching function, which switches the detector on and off. We choose a switching function which has a Gaussian profile with a long time of interaction, a monopole moment operator, and a quantum field operator. We assume that the initial state of the whole system is given by the following formula. So this is the ground state of the detector, some state of the field, which will take to be either Unruh or Hartle-Hawking state, and a superposition of static classical trajectories. Now, we fix the beginning and let things happen. So we let the detector interact with the quantum field and look at the final state of the detector after the interaction with the field. We work in the first order perturbation theory, and final state of the detector is obtained by taking the final state of the whole system and tracing out field degrees of freedom. That's what we get. Slightly complicated expression, but I will just briefly explain what individual terms mean. So the first term is just the initial state of the detector. So it corresponds to the situation in which nothing happens, there is no excitation, nothing interesting. The second part is the sum over the diagonal terms with Planckian probability distribution, each with Hawking temperature. So this term is the sum of contributions from Hawking radiation effect to each trajectory separately, and these contributions are combined in an incoherent way. And finally, the most interesting part is the last line, which is the sum over the non-diagonal terms corresponding to the coherences left in the state of the detector after the interaction. So we find that in general, these coherences will be non-zero. And in this long expression, the really interesting part for us will be the coefficient lambda, which we take to be a measure of the coherence. And we find that this coefficient is given by such a formula. So this is just the normalized inner product between two states of the field, two different states of the field, left after excitation of the detector on two different trajectories to two different energy levels. Moreover, we find that lambda is 0 unless this specific condition is satisfied. Here alpha n and alpha m are the gravitational time dilation factors on the trajectories n and m respectively. And this condition means that the energy of excitation as perceived by any static observer on two trajectories must be exactly the same. So why are we interested in this coefficient lambda? As I mentioned, this is an inner product between two different states of the field. If this is non-zero, it means that these two different states of the field are not fully distinguishable. So the situations where we absorb a particle on trajectory m and to some energy level and on trajectory n to some other energy level, these two situations are not fully distinguishable. And what can be the reason of such non-distinguishability? Well, they are not distinguishable because on two different trajectories we can in fact absorb the same particle. So in particular, if we fix one of these states, say this one on the right, this tells us on trajectory M we absorbed a particle to the energy level EJ. If we fix this state and require that this condition is satisfied, lambda will tell us what is the probability to detect the same particle on some different trajectory. And in such setting, lambda becomes a function of only two parameters. This is the radial distance of the other trajectory, when we have one fixed, and the angle between these two trajectories. We have a spherical symmetry in the Schwarzschild spacetime, so there are only two parameters. And we can plot this lambda. So in fact, this is the shape of the particle if we take the initial state of the field to be the Hartle-Hawking state. So what we see is that we have a relatively sharp peak in the middle around the trajectory M. We have some small oscillations in the angular direction, some oscillations in the radial direction for r greater than r of the trajectory M, and we have a relatively large peak on the antipodes. So surprisingly, if we detect a particle on one side of the black hole, it is we have relatively high probability to detect the same particle on the other side of the horizon. Now, if we consider the Unruh state of the field as the initial state, we get this instead. So again, we have a peak in the middle corresponding to the trajectory M, and oscillations in the angular directions with a relatively large peak on the antipodes again. But now the peaks are extended in the radial direction. Is it strange? Well, not really, if we recall that Hartle-Hawking state corresponds to the thermal buff around the black hole, thermal buff of particles. So particles are swaying around some positions which are defined. While Unruh state is the state of outgoing flux of particles. So particles are going away from the black hole. So if you absorb a particle at some position, you can as well absorb it further away at the same angle from the black hole. And that's it if it comes to our results. There are, of course, many more interesting questions to ask. Some of them are written here, so one can try to do the same thing with other kinds of trajectories. So we did it for static trajectories on Schwarzschild spacetime, but one can try to consider detectors in superpositions of some other trajectories, some moving trajectories. One can also take a look on other spacetimes. So Schwarzschild spacetime corresponds to a neutral static black hole. One can see what happens if you consider a charged black hole, a rotating black hole. And finally, one can try to reinterpret our results in terms of quantum reference frames. So we view the situation as a black hole and a detector in superposition of trajectories. Within the quantum reference frame formalism, this should be equivalent to a particle with well-defined position and black hole in superposition of locations. That could be interesting to think of our results in these terms. That's it. Thank you.
Okay, thank you, Jerzy. Do we have any questions?
So if you think of classical particles moving outwards from the horizon, not just radially, but in all possible directions, then what would the paths be? Like, could this be a classical effect of particles moving around the black hole?
I think that, yeah.
Third talk over there.
Yeah. So,
Particle will move around geodesics, and the geodesics are not necessarily radially outwards.
That's true. That's true. Yeah.
Just classically sort of focusing on the other side.
I don't know the I don't know the answer. Sorry.
So I got a bit confused because a detector often for me, I think that is what somehow take information from the microscopic world and give it to us in there. But now I see this more that actually what you do is that you have a quantum system that you put in a superposition that you entangle with your back. So is that how I should see it? Because you have unitary time evolution, I guess. Was it when you say that if I can detect the information here, but then I can also detect it here? For me, the measurement collapses either or. But actually, what you do is to entangle these systems and see.
Yeah.
Entanglement or something like that.
Yeah. So I consider a quantum detector. I mean something similar to the Unruh-DeWitt detector, but not necessarily two-level system. We have many energy levels, and we look on what trajectories this detector does not get fully entangled with the quantum field throughout the.
The coherences are large.
Yes.
Yeah.
Yes.
Do we have any last questions?
Yeah, just for a quick one. Because the interesting thing here, I guess, is that having a multi-level detector means that there could be this condition that you can have a different excitation that's relative to alpha is the same value. So if you just consider the usual Unruh-DeWitt detector with just one excited state, we always have zero these lambda coherence terms, or just
so in our situation, around the black hole, if you consider the trajectories at the same distance from black hole, then this condition that I mentioned is satisfied even if you have only one energy level. This was not true in the previous work of Lewis, where they considered Unruh effect, and they needed more internal energy levels. Now, at this one radial distance, one energy level is enough. But if you want to consider more various distances, then you need more energy levels.
Let's thank Jerzy again. And our next speaker will be Bo Sundborg. So Bo Sundborg will be discussing a simple model of a black hole and its radiation.
This is the microphone, so you can...
Do I put it here? Okay. Is that working? Okay. All right, and this is a pointer or something? No?
Yes, so you can go...
Ah, yeah, okay. All right. Nice to be here. I am from a slightly different community, but I think the issues you're discussing here are very interesting. And I hope now that interest is a bit commutative. I'll try to make it interesting, at least for you. So my community is ADS-CFT holography, but I think there are important and unexplored, I should say, points of connection, and I'm very curious about those. So let's see. All right. I start with a takeaway, so we'll get at least something out of this talk, hopefully. So I claim then that standard quantum mechanics, at least in the form of quantum field theory, can model, I'm not saying it is actually, quantum effects of quantum gravity, but it's a useful set of models. It provides a useful set of models. That's my first claim. And in this context, I've found that composite objects, well, we know that. They probe tidal effects of gravity. We know that because the moon and the Earth are composite objects, and they definitely show tidal effects. But even more interesting for us here, perhaps, this holds at a quantum level as well. Finally, I will not say black holes, but black hole-like objects can also be modeled in this framework by looking at thermal equilibrium. And in a particular environment, what I would call a gravitational cavity, which we call, in this field, we call that anti-de Sitter space. Of course, it's interesting to go beyond thermal configuration, thermal equilibrium, consider pure states and how they are entangled, and if eventually you can thermalize, etc. There is some work on this, but I will not discuss that. And also, I will not discuss the radiation. I would have wanted to, but it got too complicated. It will be an exercise for next time, I think. Because I think I have to cover some material in a crash course in 5 minutes or so on holography. That is a field that has developed for 20 years. I think it's possible, but let's see if I can do it. All right. Yeah, this is the idea that yeah, it does look a little bit grayer on the. There's not much difference, but the middle item here, composite objects, is I thought was. I mean, I saw similar things in the abstract, so I wanted to connect to that because it's very natural in this framework. And what you can see is how objects coming in states are in one state and out states are in another internal configuration. This is what tidal effects do. They convert one state to another one, which is pretty nice as a way to detect the presence of interesting gravitational fields. All right. So what do I want to do with this talk and what do I don't want to do with my research in this field? Well, I like a kind of operational approach. Define gravity, not by some unobservable object like a gravitational field, right? The gravitational field is not observable. We all know that, or we should know it. It's not directly observable. It's like a gauge field. Depends on coordinates, etc., etc. So define gravity by measurable quantities. I would say, what is a measurable quantity? It could be Green's functions of a quantum field theory, for instance. Related to this, would some background independence. It's difficult in gravity to distinguish between what gravity is and what is our choice of reference frame or system. So the safest way to me is to look do the actual measurements at weak fields, which is usually at infinity, far away from the sources of gravity. Then you're pretty safe. This is a time-honored principle in, the origins of my field is particle high-energy physics, scattering theory. And there's still some truth in it, right? Even if it's old, it can be some truth. Now, as I said, I want also to probe gravity by composite objects. And for me, they will be represented by composite quantum field theory operators. I've crossed over Unruh-DeWitt, and that's not really kind, is it? I think it's a brilliant idea. I'm sure, yeah. I think we need alternatives. Let's put it that way. What I will replace them will certainly have deficiencies, but again, there are different perspectives, and maybe having different perspectives can help getting a better picture of the whole field. All right, again, as I said, reliable detection in asymptotic regions, that's what I'm going to focus on. Detectors of composite objects, well, in a way, they're more composite. They have more states, just like in the previous talk, an infinite number of states in my case, but you will only access a few of them in practice, of course. Yeah, the detectors in this case are very quantum, right? So it's violating some principles that are cherished, but it can also lead to interesting, I mean, of course, objects are quantum, so that's fine, right? But it will be a bit different. So, for instance, I will not specify trajectories for the detectors. They will propagate just like any particle. They are particles in a sense. Particles that can be excited. That's my detectors. They can be detected by ordinary means out at infinity. And moreover, detectors are made of the same stuff as the fields that they detect. This is both a consistency condition, but also very annoying at times because you have very little freedom in building your tools. But that's it. So the idea is to represent gravity by quantum field theory. And that's done in this subfield of high energy theory that is called ADS-CFT. So what is that? It's an observation connecting results in gravity and quantum field theory from 1997 or 1998. And it's still a conjecture. although evidence for it has been accumulating steadily, and there is not really any counterexample. There may be a few doubts here and there about the scope and various things, but it's actually extremely successful to the extent that it's becoming a bit boring, but it's a body of knowledge that is quite extensive today, and we can make use. I will not make use of all of it, definitely. I will also not show you all the calculations, but trust me, the part I'm using of this body of knowledge is quite simple. And what are the simplest fact of these? What is ADS? It's anti-de Sitter space, if that tells you anything. And CFT is conformal field theory. So let's talk about these things for a moment. Well, I think ADS is essentially the gravitational equivalent of a harmonic oscillator. It's sort of the simplest space-time that confines a particle. It has constant negative curvature, and it confines the motion of all waves and all massive particles. That is good for some things, as a theoretical laboratory. It's not so good for the Hawking radiation that I avoided. That's why I avoided it. Of course, you can technically deal with it, but it will become complicated. And because it confines, it's effectively a cavity, which is good for thermodynamics, for instance, and also for quantum mechanics. It's just quantum mechanics. And ADS has a natural conformal structure at infinity. That is math lingo for that. You can control light propagation in a simple way. Here is just a picture showing spatial slices, that's constant time surfaces. It's a hyperboloid, essentially for time-like vectors in Minkowski space. That has the same geometry as ADS. But then you usually, when I draw things, and I will do that several times, I've already secretly drawn things for you. I've drawn the spatial slice as a disk. Straight lines or geodesics on that time slice are actually circles which are orthogonal to the boundary. That's the geometry. We don't need that in detail. I just wanted to show that this is concrete. It's a very simple structure. And spatial infinity will be like a sphere at infinity out there. Okay. All right, that was ADS. That's all I will tell you about on ADS. Conformal field theory. Conformal field theories are the simplest interacting quantum field theories in many sense. They don't have an energy, they don't have a scale in themselves. They can get a scale when you put them on certain geometries, but they don't have an intrinsic scale. They require not a metric or way of measuring distances, but angles or light rays. Then they can do well. They are defined by spectrum, like any quantum theory. I will not, by the way, this is just to show you that there is a framework here. I will not use details of this, except that there is a spectrum of operators that are interesting in each conformal field theory, characterized by spin and the quantum number that is like energy, but it's scaling dimension actually, because there is no scale as such. And then all the interactions in this theory are characterized by couplings of three operators. That's all. that defines everything about this conformal field theory. So it is simple. Actually, the theories I really use are going to be free field theories. So I don't have to deal with all this structure in the calculations behind what I'm telling you about in the actual examples. Yeah. That was CFT and that was ADS. And what is ADS CFT? That is this connection between the two. The geometry in ADS is such that out at infinity we have a sphere. On that sphere we have a conformal structure. You can have a conformal field theory. So everything that happens on the boundary out here. Now, remember, this is infinitely far away, but I use this like stereographic projection to a disk. If we are interested in the kind of processes I talked about, namely things that are happening far out at infinity, where the gravitational fields are weak, if we do that, we can make use of this to the full extent. And out there, it's quite easy. Was the first things that were done in this field that you could match operators in on the sphere with fields inside of ADS, one-to-one. That's a dictionary. So that means that Green's functions, at least asymptotic Green's functions of the asymptotic regions of anti-de Sitter space are directly related to other Green's functions in the conformal field theory. So let me repeat that. There's a direct mapping between Green's functions in gravity that we are interested in and quantum field theory, standard quantum field theory, only that is on a sphere. So we want to calculate these Green's functions of certain operators and obtain sort of a scattering theory in anti-de Sitter. That's the idea. It's here, right? Operator out here, operator out there, in, out. That's like a scattering process. What happens in between? That is mediated by anti-de Sitter space, but it can also be calculated directly in a quantum field theory. So, yeah, so to get back to the takeaways, there is a connection, hopefully, between the takeaways and the content here. I've been saying that standard quantum mechanics in the form of quantum field theory can model quantum effects of gravity, for example, around black holes, right? There was a check mark there. All right, black holes. Black holes have an event horizon. My point here is really that the most interesting thing with black holes and the most things that is going to survive is really not a horizon, because it's not clear that there are horizons in the quantum theory. But there are going to be photon spheres where photons can make circles around, a bit outside the horizon. So whether there is a horizon or not is not clear, but there is something else interesting that can be studied, and it can be studied in quantum field theory, as I've been claiming. So how do you make black holes in this quantum field theory? Well, we know that black holes are thermal objects in a sense. They emit Hawking radiation, they have entropy. In flat space, thermal equilibrium is unstable because temperature actually decreases with mass. In ADS, at least if they are big enough, black holes are stable, and that happens above a certain Hawking-Page phase transition. That phase transition does have a match in quantum field theory as well, so this whole structure survives. That's the point. ADS is also good for thermodynamics, since we have no divergences from counting of states, because we have a nice box cavity. All right. So we got black hole-like objects. Now we want to study composite objects as probes. Well, test particles are not so interesting themselves, but if they are composite, they are more interesting. They are clocks, and I think Igor and Magdalena and others here have been making a lot of progress on looking at this. So the clocks will sense gravitational time dilation. But if you also look at their internal structure, they experience tidal forces. That can be studied in this framework, and that will fulfill the next checkbox. We can tie this together by considering these composite operators in quantum gravity. Now it's getting fast and sketchy. Composite objects are actually dipoles. You can study dipoles. They have internal excitations. To do that technically, you have to take a few limits. Make it messy, but makes it possible to calculate Green's functions between the lowest state, which is, I written that up, is the density essentially, and energy density. It's the lowest excited state. And if you calculate such a correlation function on the boundary, you will get the tidal excitation of a probe traveling through space. This depends on temperature. And therefore you can also see the effects of black hole-like states on tidal effects. Here they are. We can transform to momentum space, and I suppose the outcome is that higher temperature or mass yields conversion at smaller angles, which actually means that the object, black hole-like object, is larger, as you can see by considering what geodesics are in this asymptotic space. They are like circles which are orthogonal to the boundary. So if you have smaller angles, getting conversion between nearby points, smaller circles, means that the object that disturbs the propagation is larger and larger, forcing the gravitational effects closer and closer to this boundary. Yeah. Behind all of this is free quantum field theory with the constraint that you are dealing with charges, right, on a sphere. So it's super important to find all these effects in detail to impose the Gauss law constraint. Once you've done that and do all your partition sums, correlation functions in free field theory, those correlation functions I showed you drop out, and you find these nice results, other results too, that connect free quantum field theory with a large number of charges, colors, whatever you call it, fields, is similar to gravity. Not exactly gravity, but similar. And, well, you've seen these conclusions before, so I will not repeat them. But it's a framework, at least. It would be interesting to see how it connects with more This is not proper quantum measurements, but we have a framework, at least. Thank you.
Excellent. Do we have any questions for Bo?
So is it correct to say that the correlation of the ONs of the operator O is the same as the correlation of the fields to which they are dual, the gravity fields that they are dual? Is that the correct statement? Or?
I don't remember, to be true. To be honest, I mean, they are directly as a one-to-one correspondence. So I mean, you have one, you have the other. That's the only thing I really care about. There is some sort of wave function factors. That's a one-to-one map. You can get one from the other.
And so the composite operator is not the one that lives in the gravity picture.
Well, they are the same essentially by this map. I mean
there is something else.
Yeah.
The energy density.
I mean, on this slide I show what the standard way to talk about this is that to each operator in the quantum field theory, there is a corresponding field in the gravity theory. For instance, energy density, it's obviously connected to energy momentum in some way and connected to a component of the graviton. So this is, and then there are more operators. There are zillions of operators, but the lightest are the most important ones. And I should say, I mean, I think that is something to emphasize. These, it's a completely different language in a way to what I think most of you are used to, but the objects I'm talking about are actually just bound dipoles, and they are one state here corresponding to the graviton is just a state of it's an excited state of another object. So this tower of fields that we have in the gravity theory, that is actually directly corresponding to ground state and excited states of composite objects. You can just compute their energies in ADS if you like. That's it.
Let's give another round of applause for Bo. Our third speaker is now up. Just quickly introduce you.
Yeah.
So for our next speaker, we'll have Sofia Qvarfort talking about gravimetry through nonlinear optomechanics.
Thanks. See if I can. I should be okay. Well, I'll find out. I think I click the button. Does it still work? Okay, cool. Great. So thank you so much, and thank you to the organizers for inviting me to give a talk here. So this is also interesting in the sense that this maybe provides a slightly different picture. And I'm sad to say there won't be much relativistic stuff in this one here, but there will be some gravity. So in this one, I will talk a little bit about research that I started during my PhD and have been sort of building on since then. Gravimetry means the sort of measurement of gravity. Usually that's just gravitational acceleration. And then we have nonlinear and optomechanics here. And I hope for those who are not super familiar with this to provide a bit of an introduction for each concept. And also to talk a bit about tools that we use when we want to ask things like how can we measure gravity, what is the fundamental sensing limits to gravity measurements. Okay, so my name is Sofia and I'm here doing a Wink Fellowship at Numerical. Okay, so what is precision gravimetry and why do we care? So first of all, for example, we have this gravity map here of the Earth. So here you can see deviations from some standard median gravity or average gravity field. And what you can do with this is you can sense, you can essentially see where you have these gravity anomalies. And this enables you to do things like track things you couldn't normally track very well, like meltwater, which you can't really see, for example, from space. So this was made using a satellite from space. And it allows you to, for example, track the mass of water as it moves around. On the other side, so this is very sort of technological application. On the other side of things, we're very interested in, for example, can we measure the gravitational field of really, really small masses? Because this would allow us, if we could actually push this all the way down to where we have masses that are in superpositions, that could enable us to start asking questions like, what does the gravitational field of a superposed mass look like? Which we don't actually have the answer to. So I don't sadly have the reference here, but this was work done in Vienna just a few years ago, and they measured a milligram mass, which is the gravitational field from a milligram mass, which is the smallest mass we have measured so far. And then also we have things like, gravitational wave detection, which really allows us to probe very fundamental aspects of physics and has opened up a new way to actually do astronomy and cosmology by detecting gravitational waves. We also have the notion of modified gravity theories. So there are certain problems, for example, the cosmological constant problem, that predictions from GR and quantum field theory are very, very different. And in this sense, some of these modified gravity theories, they propose ways to solve this problem. So I'm by no means an expert on this, but here you can see a bit of a zoo of all of these different proposals that have been put forwards for how we can modify gravity while still retaining some of the observations that we have on sort of solar system scales. And the question here is, if we can measure gravity extremely precisely, could we rule out some of these or all of these worst case scenario theories that help us solve these problems? And the way we want to try and measure gravity is through something I call, in this case, optomechanical systems. So here's a picture taken from a lab in London at UCL. And this here is a levitated nanosphere. So this is levitated against gravity in a Paul trap, which means you have some rotating electric fields. And this is being illuminated with a laser. So these particles are usually super, super tiny. They weigh maybe 10 to the minus 15 kilograms. And what we're going to use them for is we're going to use them as sensors, and we want to measure gravity with them. So just a little bit of what are the ingredients that go into this. So optomechanics, opto means light, mechanics means mechanics. And we need some kind of mechanical element. So in the case I just showed you, that was a levitated particle. But we can also have other things like mirrors and clamped systems, membranes, and so on. And then we need some kind of probe system or a cavity mode in the case of a confined system that actually interfaces with this mechanical element and which allows us to read it out, because we can't usually, we need some other system to act as the detector onto the mechanics. And when we put these two together, we get the most massive quantum systems that we have in the laboratory. And this opens up quite interesting questions. So one of them is what I mentioned before, can we put these systems in quantum superpositions and measure the gravitational fields from them? That's a really interesting avenue. We're going to take the other route and ask, if we use these systems as detectors, how well can they help us measure external gravitational effects? So here, the system is just a probe. It's not the source of the gravitational field. And the optomechanics, as I mentioned, they come in many different sizes. So for example, here to the left, we have some membranes and clamped systems here. Here we have these levitated nanospheres, and this publication here was the first to show that they can be ground state cooled. Here we have two drum systems which were entangled, so we are starting to see really interesting demonstrations of quantum control of these mechanical systems. And then here finally we also have a superconducting levitated systems which can reach very high masses and a very sort of low noise systems. So this is really exciting. We have quite a plethora of different, a large variety of different platforms, and all of them have different advantages and disadvantages. And I'm not going to, but lucky for us, if we do theory, most of these can be described by exactly the same equations, and that's what we're going to do now. Okay, so how do we interface light and matter in this way? So we're going to go to second quantization and describe them more or less, so confined harmonic oscillator systems. So in this case, we have here one of the simplest optomechanical systems. So we have a cavity with a moving end mirror. So we put one of the sides of the cavity on a spring. And as we shine light into the cavity, the light pushes onto the mechanics, onto the mirror. And that in turn changes the resonant frequency of the cavity. And that changes the way the light behaves. And to lowest order in the interaction here, we can write down the following Hamiltonian that decides the dynamics here. So basically here, this B dagger plus B, that's your X, that's your position, center of mass position, and A dagger A is the number of photons. So the number of photons displaces the mirror, which changes the resonant frequency of the cavity. That's the kind of intuition you want to keep with you. This kind of dynamics of these systems, this was solved back in the 90s, in 1997. There were two papers that looked at these, if you have purely quantum systems, what happens because you solve the dynamics, and they show that you get these really interesting cat states of the light. You can also get cat states of the mechanics. And the key thing, just lingering a little bit here, is that here we have three operators multiplying each other. So we had before, Robert was talking about linear Hamiltonians, linear interactions. In that case, you only have two operators multiplying each other, and then the equations of motion become linear. In this case, that's not true. So we have three operators, and that means that the equations of motion, they become nonlinear. So we often talk about nonlinear dynamic system in this case, and that's where the nonlinear optomechanics comes from. In many cases, to describe experiments, you then go on to actually linearize these dynamics. You drive the optics very hard, and that gives you easier mathematics. But we want to stay in this regime, A, because it's the fundamental regime, and B, because we actually see some sensing advantages in this regime. Okay, so that is, we've talked about the systems that we have. So then what tools do we use as theorists to talk about quantum metrology? So then the question is, how well can we measure something, an external effect like gravity? How well can we use our quantum probe, our quantum system, in order to do that? And what we want to introduce here in this case is something called Fisher information. So there are many ways to talk about quantum metrology, but if you want to capture quantum effects, the Fisher information allows you to do that. So it's a bit, the definition is that it's a measure of how much the state changes, how much information you can get from the state as it is affected by something external. So here we have this I of theta. Theta is the parameter we want to measure. It is an integral over these conditional probabilities. So given some measurement outcome x, the probability of measuring some measurement outcome given, or also based on the value of your parameter is given here. And it has this sort of unintuitive form, but it comes from, I believe, like taking the variance of the score, which is, or taking the score, which is something like the variance of the maximum likelihood. So you can, if you look into fundamental notions of estimation theory, the quantum Fisher information drops out as a very natural measure. So in our case, these probabilities, they're given by quantum measurements. So we define some P over M, this pi x. It can be continuous or discrete, so the x are measurement outcomes. And our state has encoded somehow the parameter theta that we want to measure. So how you encode the parameter depends a little bit on your case. In our case, we'll do it through dynamics, but you could also do it through like gates or operations. But this is the classical Fisher information. We do quantum science, so we want to go quantum. What you could do here is you can say, okay, fine, I have one quantum measurement, but I could ask, what is the best quantum measurement? If I then optimize over all possible measurements, I get what's called the quantum Fisher information. And for pure states, this is quite a nice expression. We just differentiate the state, which depends on theta. We differentiate it with respect to theta, and we compute this quantity. If you have non-unitary dynamics, things get hard. That's it's a lot worse to deal with this, but at least on in this level, it's very, very nice. And what really is the key property of the quantum Fisher information is this relation to the Cramér bound, which actually relates the Fisher information to the variance of your parameter. And here, the intuition here is that the variance of your parameter, you want that to be as small as possible, because you want the same value all over again when you measure. And so this M here, this capital M, that's the number of measurements you perform. So if you had infinite time and infinite funding, you could take this to infinity and you still get zero variance, but we never have that. So we want the Fisher information to be as large as possible. So a lot of quantum metrology, the goal is to compute the Fisher information, find the optimal measurement, and then see what is the fundamental limit that you can have for your variance. So just to give a little bit more intuition, the Fisher information can also be seen as a measure of change. So if you take your initial quantum state and you say, when affected by this parameter, it would evolve here. But if for example, gravity wasn't present, it would go here. The quantum Fisher information is basically the distance between the two states. So to some extent, it's related to state discrimination. And I also wanted to connect this a little bit with some words or phrases that people throw around a lot in this community. And one of them is the standard quantum limit. So this appears a lot when you talk about gravitational wave detection. And here the standard quantum limit is basically a classical limit. Because you can see a lot of works that say, oh, we go beyond the standard quantum limit. We break the standard quantum limit. And that's very nice in the sense that the standard quantum limit is given, it's always proportional to 1 over n, where n is the number of probes in your system. So say you have a very strong laser beam, you have n photons in that, then that's the standard quantum limit is set by that. And it's always a balance of what is measurement backaction noise and shot noise, essentially. And shot noise has to do with the fact that photons have intrinsic uncertainty. And measurement shot noise has to do, or measurement backaction noise has to do with the fact that when you measure the system, you disturb it. So if you measure position, you give it momentum, which then also changes position and so on. So the standard quantum limit is set by the sum of these two. And in order to break it, you need quantum resources to do so. You need squeezing or you need entanglement. This should be contrasted with something called the Heisenberg limit. So people often talk about this as well in quantum metrology. And when they say, sometimes they say we break the Heisenberg limit, and that is usually not correct in the sense that the Heisenberg limit is a hard limit. It's set by the energy of your system, and the more energy you have, the more this limit changes. So if you increase the number of probes in your system, the number of qubits, if you change the Hamiltonian, this limit also changes. And this is where having access to nonlinear dynamics is quite interesting, because I've written here nonlinear interaction contain more energy. I thought about that and then I uploaded the slides and then I didn't have time to change it. So not necessarily correct, but the energy eigenstates scale differently, higher, with the number of, for example, photons in your system. So your energy levels are different. And what happens here is that when you then compute the Heisenberg limit for this kind of Hamiltonian, then you get that this is proportional to 1 over n squared. And that should be contrasted with 1 over n in the classical case. So here we also have this like nonlinearities are useful for sensing. But only certain states, only really quantum states, like superpositions of Fock states here, will achieve this limit. So it depends both on your Hamiltonian and on your states. Cool. So we now have some tools. We have quantum metrology tools. So in the last bits here, I'm just going to go through what we have done a little bit here with these, considering the fundamental sensitivity of measuring gravitational acceleration. So here, let's take our optomechanical systems. Let's plop the Earth next to it. This would be like, say, you have your system that's horizontal and then you flip it, so it feels gravitational acceleration. And to first order, we can just approximate this as mgx. And we can add that into the dynamics of our system. And then the question is, we encode this g, that's what we want to measure, we encode that into our system, and it couples through the mass of the mirror here. So the larger the mass, the stronger the coupling. What question is now, how do we compute the fundamental sensitivity of this? So we can also do, instead of the Earth, which might be that's static, it's always hard to measure, we can instead take a golden sphere, for example, like a really heavy material, and we can shake it next to the system. And in this case, we get a time-dependent coupling, which looks like this. And here we have the distance and so on between the sphere and the system. And how do we do this? So we use a Lie algebra method, because this is nonlinear dynamics still. This is harder than using, for example, phase-space methods. And I'm not going to go into that. But basically what that allows us to do is to decouple the evolution operator into different exponentials. So what this allows us to do here is it gives us a recipe, and just to go through what the different terms here mean. So this here is this nonlinear Hamiltonian that I showed you, the self-Kerr interaction it's called. Thank you. And these two terms here encode gravity, and these two terms, they encode the optomechanical interaction. And what we can do with those terms is that we can basically compute this quantum Fisher information conditioned on measuring little g. We find that it looks a little bit like this. This is not super intuitive, but we have some derivatives of these coefficients that we derived. And at certain times, we have some nice decoupling of the system, and we can basically look at this variance of g, and we find this expression in terms of some experimental parameters. The interesting bit here is this delta A dagger A. That's basically a variance of the number of photons that you have in your system. And here, if you input a squeeze state, then you do quite well. A coherent state will also do well, but not as well. And the most exciting state you could put here would be a Fock state, which then satisfies this Heisenberg limit. But creating really good Fock states is very hard. So just to show you some numbers, so here we computed two different sensitivities. These numbers are for a levitated system. But if you increase this mass here, you could also increase this a little bit. And to compare, I think 10 to the minus 9, 10 to the minus 10, 11, that's what you could do now commercially. So what this shows here is that you would have to amp up these parameters a little bit if you wanted to fundamentally do better. So now this is without noise. So that means that if you had noise, this would be worse. And so that's always something that's always more layers to it, the closer you want to go to experiments. I'm going to very quickly just show you also, we can then ask questions about what about modified gravity. In that case, we have a Yukawa-like change to the Newtonian potential. We have this alpha and lambda, and they are very small parameters that change the shape of your Newtonian potential. These are the current bounds of alpha and lambda. As you can see, it's very hard to constrain here where you have very small things. In our case, we can compute that if we say, okay, we just want to measure gravity really precisely. We find these bounds here, where in this case, we also look at if you have a sort of finite size of your system, what does that do? In this case, we looked at a specific theory called the chameleon theory, where matter shields this additional modification to gravity. We also imposed these existing bounds onto these new ones that we found, the yellow and the orange arrows. In this case, we do quite well, but in this case, we found that even if we push the parameters quite a lot, we don't do super well. So we would also have to increase the experimental parameters, so engineer them to be better in order to do much better in this case. Here we do quite well because we assume a very pure vacuum in these systems which can be done, but the mapping from here to here, even if there is one, is quite non-trivial. And then finally, a sort of next step. So all of this has been without noise, and the current effort has been a little bit to try and say, okay, so we have light that leaks from the cavity, we have noise that affects the mechanical element, where we couple the position of the elements to some noise modes. Can we import these? Can we solve the dynamics still in these conditions, and then compute sensitivities in these less than optimal cases as well? So with that, I'm not going to read out the summary, because I think I'm basically out of time. Yes. So I want to thank you for listening, and I just also wanted to mention that we've just written a review on testing these gravitational effects with massive quantum systems. That's currently on the archive, and we're really keen to get feedback on this. We especially want it to be accessible for students and people who are new to this field. And this RQI crowd seems like the perfect crowd to ask for this feedback. So if you have any pointers for us, we'd be very grateful to hear them. Okay, thank you.
Excellent. Are there any questions for Sofia?
So you set bounds to how good you can measure, but what is it that you actually measure?
Yes, I didn't go into that very much. So in this case, we computed the quantum Fisher information, which means that you're just saying there is some optimal bound on these, and we can compute that, but it doesn't tell you which measurement is the optimal one. So when we looked into it, we found that doing a homodynamic measurement of the light satisfies this bound under certain conditions. For example, you needed systems they entangle, so light and mechanics entangle, and then they decouple. And this kind of decoupling entanglement method, it only happens in certain circumstances, like how strongly they couple. And under those circumstances, a homodynamic measurement is the best measurement because it measures phases. And the gravity is essentially imparted onto the light as a phase shift. So that is a very good question. But for better measurement, that is still to be discovered, I think, yeah.
Do we have one more question, maybe? A quick one? No? Okay. Oh, yes?
Yeah.
So in the previous talk,
yes,
we heard about coupling relativistic systems to non-relativistic one. So this is, of course, coupling a relativistic system to a non-relativistic one.
Yes,
that doesn't make any difference for the energy, for the energies you are working with.
No, so I would say everything here would be very non-relativistic in the sense that if you started to look at really super high masses or curvature effects, you would have to do additional approximations. There's also the subtlety of using the Schrödinger equation, which is what we do here. So if you wanted to do properly relativistic, you would have to go Klein-Gordon, describe these systems as fields rather than that. So in order to use the Schrödinger equation, we need to stay in a single inertial frame where time is well defined. Yeah, so that's definitely, you could add curvature, for example, here as sort of additional perturbations to the Hamiltonian, but you would have to make sure that you stay in a single frame to perform your measurements. Yeah.
But the effects will be beyond your accuracy limits.
That would have to be determined, I think. So you could add second-order terms into the Hamiltonian, and then you can ask, if you then evolve the dynamics, you can ask specifically how sensitive would we be to not just acceleration, but also curve, like the gradiometry, essentially, the difference in acceleration. Yes. So no, that's a very interesting question, which would be nice to extend this framework with. Yeah.
Let's thank Sofia once again. Our next speaker will be joining over Zoom. Okay. I did join.
Hi, Evan. Hi, I'm sorry, can you hear me?
Yes.
Oh, I can hear you as well. Okay, perfect. Yeah, I'm all ready if you are.
Okay. So, yes. So our next speaker is Igor Pikovski, who will be speaking, 1 second.
Evan, should I share the screen?
Yes, you can share the screen now. Who will be speaking on a quantum optics approach to testing the GRQM interface.
I think the sound is coming from the laptop.
Can you try speaking again, Igor?
Yes, hi. No, I was just asking if I should share the screen.
Is it not working?
Oh, can you guys not hear me?
Do we know why it's not working?
Because you're, do you use just...
Yeah, are you connected through the...
No, I'm connecting to my laptop.
Yeah, we should join.
Yes.
We don't have to do this.
So we can't hear Igor at all. I think Igor is very confused.
Yeah, so we can...
So with this system, and that will allow us to hear through the speakers.
Small technical changes even.
No problem. Yeah.
Can you just explain what's going on?
Yes, so we're just changing over to the room computer to connect by Zoom.
Of course, sure. We can try. So you can't hear me, right?
We can hear you, but we can't hear you from the audio system in the room. You're coming through on my laptop.
I see.
Zoom will have an echo.
You might have to mute your...
And turn off your video as well.
If you're streaming to YouTube from Zoom, then this should still...
And turn off.
Yeah, I'm connected to the room. So
turn off your video.
Why?
Turn off your video.
Wow, why? Because we will show ourselves from that camera. Why? I don't understand.
Okay.
We will show everyone here.
Okay.
Join with the computer audio.
Yeah,
can you switch off your speaker?
Can you actually disable the video for the YouTube thing? Because I have to because I'm like streaming the yeah.
Hi everyone. Not sure if you can hear me now.
Yes, we can.
Oh, you can? Okay, that's great. I had a brief glimpse, so I saw some of you.
Do you want to ask him to start sharing screen?
Igor, can you share your screen, please? And we can begin the talk, and I'll reintroduce you.
Perfect. All right. I hope you can see my screen.
Yes, that's fine. Excellent. So our next speaker is Igor Pikovski, who will be speaking on a quantum optics approach to testing the gravity quantum interface. Take it away, Igor.
Yes, thank you. Thanks a lot. So I apologize. I was not able to be there in person, but I appreciate the opportunity to connect this way. I first want to really thank Rick for organizing this really wonderful RQI circuit. I'm enjoying it very much, and will also follow up on some of the talks that I had to miss so far, as well as, of course, thanks a lot to Germain, Vasileios, and Evan for making it possible in Stockholm. So the PIs were asked to give a little bit of an overview of the research in the field. So the next 20 minutes or so will be my attempt to give an overview of the type of research we are currently interested in and the different directions that we're pursuing. So in summary, this is, in some sense, a quantum optics theory approach to understanding and testing the interface between quantum theory and gravity. And I will try to guide you through some of the directions in the next 20 minutes or so. So first, kind of a summary of our group is we are interested in the interface at low energies between quantum physics and gravity. And in some sense, I would call it non-relativistic RQI. In the sense that the tools we use are non-relativistic quantum theory and quantum information approach. And that combined with effects of gravity and fundamental questions about general relativity interfacing quantum mechanics. And sorry, I just have to ask, I heard a little bit, is everything all right? I'm not sure if you were trying to tell me something about
Yes, everything's working, Igor.
Okay, perfect. All right, great. So what does it mean to have a quantum optics information perspective? Kind of what are the type of research questions we're asking? One is, for example, how does gravity affect quantum phenomena that we're all familiar with at low energy theory? And what novel effects may arise? So can we test also some aspects of the quantum nature of gravity and whatever such a test would even mean, and what we can learn from that? Then finally, what can specific experiments with atomic, molecular, and optical systems, even in principle, reveal about this interface of quantum theory and gravity? And of course, there's a natural question, why do such experiments with AMO systems or tabletop experiments in general, what role can they play? And that, of course, has been addressed in some form in previous RQI talks as well. And one big motivation for that is that there's a lot of experiments in the recent decades that are really pushing quantum optics or quantum control of quantum systems into entirely new domains. One example is the development of atomic clocks, atomic technology, where over decades has been here even increasingly exponentially and even more exponentially improvement in terms of precision of measuring certain phenomena, in this case, precision of frequency. Other systems that are being developed are also atomic systems, but that can be delocalized over very large spatial superpositions, such as in the Kasevich group, Miller groups, and so forth. And other examples of systems are optomechanical systems, where you really push quantum physics into entirely new mass scales, and that can range from picogram all the way up to kilogram devices, where we can study and probe quantum phenomena. And so a natural question arises here: if one has these new capabilities in different scales, what type of novel questions about the foundations of physics, and in particular about gravity, one can ask and explore? So that is really the main core interest of our research group. And the next slide is an attempt of mine to kind of try and summarize some of these different directions on one slide. So we do focus on a quantum optics and quantum information approach from a theory perspective. And there's different questions that one can ask. One is just in general, not related to gravity per se, is the quantum control of novel quantum systems. So the question of what kind of quantum phenomena can we explore in entirely new systems, what new capabilities do such systems provide, and how can we test quantum physics in these entirely new scales? And this could be something like atomic metasurfaces, optomechanical systems, atomic clocks, and so forth. A related question is, how can we use such systems in order to gain some inherently quantum mechanical advantage? And in particular, what kind of directions do these systems provide in quantum sensing? And so this is an exploration of basically quantum advantages of systems closely related to the foundations of quantum mechanics, what it is exactly that provides us an advantage. And then one can apply these type of devices and maybe novel approaches to high precision experiments. And so ask questions about what novel aspects of general relativity or maybe alternative routes to test general relativity could we provide, such as, for example, novel type of superfluid helium resonators or atomic clocks in space. And here, this example is exploring how they can be used for gravitational wave detections complementarily and in different ways to standard approaches. Now, another different aspect of using quantum optics is more from a theory side and kind of a low energy perspective on phenomena which are usually studied in different domains. And so another example is what we look at is, for example, phenomena in cosmology or beyond standard model physics, such as dark energy or dark matter, and studying how some of these known phenomena from quantum information science, what they can reveal about our understanding of these kind of fundamental models. And so here's an example where we studied, for example, squeezing in dark matter axion models. And then kind of a large aspect of our research is studying so-called tabletop quantum gravity phenomenology. Namely, if there are some tests of some models, speculative models of quantum gravity that we can perform with some of these novel systems, and what type of input, experimental input there can be for the expected or maybe speculative behavior due to the interface of quantum mechanics and gravity. In general, focusing more on known physics, one can also ask questions about how does general relativity change some of the quantum phenomena that we know and that we can explore. So what type of general relativistic features can one actually probe within quantum theory, where GR might not necessarily be quantized, but can still have an effect on quantum mechanical probe systems. And then closely related are, of course, the questions about what indirect tests of quantum gravity can one make, what can one deduce from such experiments, and in general, what type of discussions can one have or motivations that shine light on different phenomena and different concepts that underlie gravity and quantum theory. So what can one learn from something like the Duncan experiments about it as well? So here is, for example, a drawing from George Gamow from 100 years ago, where he drew Bohr and Landau very fiercely debating about the need or lack thereof of quantization of the electromagnetic field in similar spirit back then. And then finally, I want to mention the newest result from our group, where we show and analyze that it is actually possible also to combine these questions about indirect tests of quantum gravity and gravitational wave detection in order to see some signatures of single gravitons as we expected. And I'll say a few words about this later on, but there will be a dedicated talk to that by Germain later in the afternoon. Okay, and now quickly flashing also all the people that actually do the majority of the work. So we have, often also masters and we have bachelor projects, but I do want to highlight that we do have upcoming open PhD and postdoc positions, especially for this RQI crowd. So if there is any interest, please feel free to reach out. You can just email me directly if you're interested. So in summary, we focus on quantum optics theory, gravity, and the foundations of quantum mechanics, as well as gravity. Okay, so now a little bit more concretely, to give a few examples of some of the research directions that we are pursuing. In many ways, to understand how one can ask specific questions using this quantum foundations approach is to ask very fundamental questions about both theories. So the foundations of quantum theory and gravity are very different, and they're built on very different fundamental principles that we assume to be valid. So on the quantum mechanical side, it's inherently probabilistic. There's no commutativity. It has a unitary linear evolution. On the gravitational side, it's completely different fundamental principles, such as the equivalence principle, space-time geometry, and then the fact that space-time itself is a dynamical quantity. Now, from these fundamental principles, of course, there's many more, and one can structure in different ways. But in principle, there are these different foundations, and they also result in different phenomenology. So some observable consequences on the quantum side are something like wave-particle duality, so interference of particles, really, entanglement, uncertainty relation, Bell inequality violation, and also, of course, high-energy phenomena, such as particle creation, fluctuations, and so forth. And on the gravity side, well, to lowest order, we have just the regular Newtonian force, but we have, of course, post-Newtonian corrections. But they're not just a correction to the force, but there's a metric nature to that, showing itself in unique phenomena that don't appear in other theories, such as time dilation, We also have predictions, strong field predictions such as black holes, and resulting phenomena like gravitational waves, and and very funky things like closed time-like curves and so forth. So of course, it's not an exhaustive list, but just to give a little bit of a flavor. And so one approach in this kind of in some sense, the mindset that we often pursue is, well, when and where do some of these different concepts of phenomena intertwine? And can we shine light on this? And in fact, some of these, of course, have been experimentally tested already and have been seen. And the most famous example is the interplay of the wave-particle duality or interference of matter waves in the presence of a Newtonian force. And this goes back to Colella-Oberhauser-Werner some 50 years ago or more. And this is exploited since then in many other setups, such as atomic fountains, in the Kasevich group, Müller, Tino, and so forth. There's many, many groups working on that, also just for technology development. So this is a regime that we understand well, and that we have exact experimental input where there's no speculation needed about whether things work together or not. And so just kind of as a very brief summary of this aspect is basically we know that we can add the Newtonian gravitational potential into the quantum evolution of systems. And so if we have a matter wave that's delocalized in the Earth's gravitational field, well, it will experience a phase shift to the Earth's gravitational field. And this phase shift is proportional to the separation of your wave packet, as well as the time. And the key of that is, even though it's a gravitational phenomenon, it's divided by h bar. So it's actually very large and visible phenomena, which is what Colella-Oberhauser and Werner realized. And you can see this phase shift in simple experiments, such as, for example, cold neutrons here in a Barak diffractor, where you create this type of interference pattern, and it's on centimeter scale. So you just rotate it, and then you can scan this gravitationally induced phase shift. And as I mentioned, that's of course the same fundamental principle behind atomic fountains. So what we learn from such already performed experiments is that, well, we can add gravity in the same way as we add other interactions into our description of quantum systems as an external potential. And it does change something uniquely quantum mechanical. It coherently induces a phase shift, which is given by the Newtonian gravitational field, or one can extend it even to the tidal forces and so forth, which has been recently done. What we don't learn from such experiments are two unique questions that arise when we have gravity. One is, well, gravity is a metric theory, and so going beyond the Newtonian limit is interesting because we do want to probe something that's unique to general relativity. It does not have an analog in other interactions. And the other question, of course, is what about the quantization of gravity itself? So if we have to include that in our experiments, we would be, then testing really quantum gravity. And in many ways, what we do, as well as the broader field, of course, does it with many, many groups that also talked here at RQI and others, is exploring these two different directions in different views. So modifications that allows either or both to study some kind of GR corrections and or study the questions about the quantization of the gravitational degrees of freedom themselves. And there's different ideas and many more maybe unexplored ideas how we can go into these directions. It's a very exciting field to work in and kind of still, I think, in a very, very early phase. And so let me give you just an example, a few examples, in fact. I'll briefly run through that in the next 10 minutes or so. One is, well, there is another interface we can look at. So going beyond the Newtonian force, we can look at post-Newtonian effects, and in particular time dilation, which is unique to GR, and see how that intertwines with this matter wave interferometry. And that is really something that we work with together with Magdalena Zych, Fabio Costa, and Czesław Bruckner when we were back in Vienna working together. Now Magdalena and Fabio both are in Stockholm as well with their own research groups, and still, of course, exploring these directions because it turned out to be a very rich and very promising new field where there's a lot of interesting questions to be asked. So I just want to very briefly summarize that. And of course, we spoke long ago at RQI about these things as well. So in principle, what this amounts to is a quantum twin paradox type setup. So what it means is that instead of just using matter wave interferometry as in the usual cow experiment, we also use additional degrees of freedom, which can also measure time. and then we put them in superposition as well. And so putting that in a gravitational field really shows entirely novel phenomena. And in particular, there's new effects that arise because gravity now couples to both external and internal degrees of freedom, if and only if you include post-Newtonian corrections. And there's new quantum effects. Well, what are these quantum effects? And they really just go back to this fundamental principle of Bohr's quantum complementarity, which is summarized here in these two pictures. Namely, there's interference if you don't look at it. If you look at it, the interference washes away. Okay, so there's a trade-off between visibility and distinguishability in quantum mechanics, which I just want to briefly flash. And that is really what's happening here in this kind of proper time interferometry that we proposed, or clock interference, or single twin quantum twin paradox, or something like that. And the main point is that, well, so far experiments either do these interference experiments with matter waves, or they take atomic clocks and they measure them very precisely, time dilation, but it's very well-defined world lengths. And so if you have two atomic clocks, for example, and they measure some kind of time dilation, which they do now even on millimeter scales, well, they really probe that the time evolves with these clocks with respect to different proper times. And according to the linearity of quantum mechanics, you can also take a single clock, put it in superposition, and then it will experience the superposition of different proper times. And that's kind of the key aspect that we shine light on, that this is a new type of test of the interplay of GR and quantum mechanics. And due to quantum complementarity, there is a very unique signature of that, namely that there's because of this different time dilations experienced by the same clock, there will be an effect that washes out the interference. And it's summarized here. So I'm rushing a little bit because I think I was told I have only 5 minutes left. So just to give you a little flair, there's an older work. So in principle, you can see this interface of quantum theory with post-Newtonian corrections, and there's new effects that arise, such as the modulation of your interference pattern. And you can extend it to many different domains. The periodic clocks, you can look at actually picture of clocks, which causes decoherence. You can look at photonic versions of that, where you can study different aspects of the period delay, and so forth. And then what we're recently studying with my collaborators is we're looking also at quantum networks of clocks and how such similar effects arise there as well, which we hope to finalize hopefully in the next few weeks. Okay, and then shifting gears now, well, there's other different proposals. This is what I talked about now was going in the direction of adding general relativity to the mix. Well, can we also add something about the quantum nature of the gravitational field to the mix as well? And these are very famous and popular proposals that have been done in other groups, namely by Sugato Bose, Vlatko Vedral, and collaborators, Richie Kim, Jerry Milburn, and so forth, where they explored what we can learn about the quantum nature of gravity when we interact between two systems that both source the gravitational field in superposition. And it's a very interesting proposal. Basically, it's two cow experiments next to each other, and they interact gravitationally, and that induces entanglement. And so I just, I think I'm, let me see. Oh yeah, I don't have much time. So I'll just very briefly rush through that because this has been, of course, discussed in many different fields. Our goal here was to analyze what it is that one can learn from such experiments. So one really generates entanglement. And the question is, this is an indirect test. So how is this entanglement generated? And what can we learn about the underlying nature of gravity depending on our different assumptions? And so just to mention briefly, this is what we analyzed. This is what we analyzed in this paper here more recently, basically trying to give clarity because there's debates, and all the debates stem, in fact, around the fact what fundamental principles we take for granted and what we deduce. And so all of these different answers are kind of mutually correct, depending on what starting point there is. And so in short, it is quite ambiguous about what we learn about it, depending on what we elevate as some kind of the ontology of how entanglement is generated. So you can look more here in this research paper. So what it basically shows that in the Newtonian case, it's clear we generate entanglement. And that's actually a similar test of kind of the new quantization of Newtonian potential as CMB observations that we already have. And if you take relativity as a starting point, well, there's a local and a non-local description. And in the local one, we learn about the quantization of the mediators, but of the mediators, then we have to elevate ghost particles, such as spin 0, spin 1 gravitons, that we usually don't assume can be observable, but they are the ones that mediate entanglement, where in the non-local case, one can also generate entanglement non-locally. And so it all depends a little bit about what one can learn from these experiments. Maybe one has to modify this setup somewhat to distinguish these different interpretations. Okay, and then finally, just in the last minute, I just want to say our newest work, which Germain will talk much more about, is we studied something completely different. We asked the question if it is possible to detect single gravitons as we expect them directly, real ones. And this is the interface of gravitational waves that we know in the wave-particle duality, namely the discretization of waves. And so this is a paper that just appeared a few months ago on the archive, and you can look at it here. And just as a one slide summary, it is possible to detect single gravitons. And the key ingredients for that, which we outlined, are the following. One has to focus on macroscopic quantum systems, that's your detector. One has to focus on stimulated emission and absorption of single gravitons. One has to focus on quantum sensing, in particular of quantum jumps, and one has to correlate the results to independent classical detections that can tell us what source it is that is inducing that. And with all this, it is possible to detect single gravitons even in realistic experiments. And that's what we outlined, and Germain will tell you much more about in just a little bit. And the upshot of that is, well, there was a debate, and in fact, there is an expectation, has been for decades, that gravitons are not detectable, that there is no way to do that in realistic experiments. Famous example is Dyson's paper here recently. Well, we show that that's wrong. It is possible to do it. And instead, what is the correct way to do that is a combination of basically Einstein's insight about the photoelectric effect and how that teaches us something about the quantization of the radiation, combined with kind of detectors which operate in a quantum regime, but are based not on LIGO, but are based on this kind of bar detector technology. Okay, and with that, I'll just skip this since I think Evan wants me to finish. So this will be in much more detail discussed by Germain, and I hope you tune in. And so with that, I just want to summarize. There's a few examples I wanted to give. There's many more. And in principle, we explore this interface of using quantum optics and control, and then applying that to very fundamental research questions related to the foundations of gravity and quantum theory. Okay, and with that, thank you for all your attention, and especially, of course, thank you for all the group members for making it all possible. Thank you.
Excellent. Excellent. Thank you, Igor. I think we've got time for one question. Do we have anything? Yeah.
Igor?
Yes. Hi. Yes.
Hi.
Hello, Fabio.
Hello. So what was the statement about the spin 0 and spin 1 components of gravity with producing entanglement?
Sure, just 1 second. I'll reshare. Yes, I rushed through that, and I apologize. The statement is the following. So how the core statement to learn something from these experiments is to understand how is entanglement generated. So we have systems that source gravity. We don't probe gravity. And then the question is, well, how does gravity create entanglement? And there's different pictures, which are all mutually, they're all correct. None of them is more correct than the other. It's just a choice of how we think about it. And all of them describe the same physics. And there's a local picture one can impose to say that, well, there's an exchange of particles that create entanglement. And one can show that in this particular case, for this type of setup, the dominant interaction that creates this entanglement involves only degrees of freedom in this local picture, which are not the real gravitons, so not spin 2 gravitons, but the kind of scalar and vector degrees of freedom. And this is because in this local picture, one has actually 10 degrees of freedom that one later just puts, by constraints to not to be unobservable. So instead of 2 degrees of freedom, there's 10. So this is the Bloyer-Gupta quantization procedure. But in virtual processes, such as the creation of entanglement, they can play a role. And it's in fact them that directly create entanglement. So one can use the local picture to think about it, that there's something that has to be quantized, but what one has to quantize are then spin 0 gravitons or spin 1. So like these ghost particles have to be quantized in this picture. Is that clear enough, or was it a bit too?
Yes. No. This is because I mean this is of course completely expected also because even for electromagnetism, the Coulomb field of electrostatics is not a propagating photon. It is the It is longitudinal and combination of the field components that are not physical, basically as propagating modes. And
exactly. And here it's exactly the same, except for now one has to elevate them to physical quantities because one wants to say that entanglement is generated locally.
Yeah. So they are of course always physical, but they are not freely propagating.
Right. They're not freely propagating or individually observable. Yeah. But for entanglement generation in the local picture, they are the ones that matter.
Yes.
In the non-local picture, they don't matter. So it all depends on what basically in fundamental assumptions one takes. That's why they define what conclusions you want to draw from such experiments.
So Newtonian gravity is in fact mediated by the scalar mode, which is not a propagating mode. And it's perfectly physical, of course. It's a force. Yeah. Thanks.
Well,
that's clarifies.
Exactly. I only would just caution what it means by physical because that's in the eye of the beholder. Somehow, that's our point. That we want to be just very, very agnostic. Just to say, look, if this is your assumption, that's what happens. If you think something else is maybe more physical, then you have a different interpretation of the experiment.
Okay, I agree. Thank you.
Excellent. Let's thank Igor once again. Okay, and with that, we now go for a 40-minute break. We will resume at 5:40 Stockholm time. There will be sandwiches provided outside. And thank you.
Welcome back, everybody. We continue with the last session of the workshop today. We have the pleasure to have Magdalena here talking about composite quantum particles at the interface with relativity and gravity. The stage is yours.
Thank you, Vasileios, and thanks also Evan and Germain and Rick for putting this together. We are already after 2 breaks, and they were really excellent. Really, thank you for organizing everything. I'll just okay. I hope I'm okay. Can be heard. Perfect. Yeah, since we are getting to late hours here locally, I'll move without ado. Okay. Yeah. Okay. Perfect. Yes. I will. Yeah. Given the time and also the very intensive talks we already had today, I thought to just give a bit of overview of why composite particles might be interesting. And I would like to talk also about something I usually skip, and that is why these considerations, even if we completely are not interested in any of the fundamental big questions, they might be interesting from the point of view of how they might affect or show up in high precision experiments that might be coming on the horizon. And so I joined University of Stockholm only in February this year. We are starting up a group, so I already have 2 PhD students, Germain and Jerzy, and Evan is visiting here at the end of the year from Australia, and we should be expanding to also a postdoc later in February. So yeah, this it's also a nice opportunity for me to have the chance to speak in a new place still for me. So the research that I typically am interested in, I think I can, at least for myself, break into some 4 different types of topics. So questions about new phenomena and testing the theory and the interplay between quantum mechanics and general relativity. So this is something I'll talk a little more today. The questions about the notion of temporal and causal order, again, and the interface between quantum physics, relativity, and general relativity. Have some interest also in alternative theories, mostly from the perspective of how different desiderata between models actually, whether they are actually embedded in the theories, and how such models can be tested. And sometimes it turns out that the direct test of the principles behind the model might be very difficult, but once the model is mathematically formulated, there might be ways to test it that are much more achievable with experiments. Again, I'll not talk about this today. And finally, something maybe has been talked more about today, and also by my collaborators from Waterloo, and that is looking at various aspects of quantum field theory in classical and quantum curved spacetimes. And so now, I think here probably there is not much motivation needed to talk about quantum mechanics and gravity, because many people have already kind of committed to that side of research. But I think it's worth reminding that while we have a lot of different and very exciting theoretical frameworks, and there are different ways that one can explore and even formulate fundamental questions in terms of experiments, what we had verified, I mean, we in terms of community, when it comes to joint quantum and gravitational effects, are only effects where gravity shows up as a non-relativistic Newtonian force. And Igor has mentioned already Cow experiments, and that's where you can measure relative phase due to difference in the Newtonian potential. Starting from 70s, it's something really really noteworthy is that it was the first time in 2017 where such atomic experiments that probe phase shift due to gravitational interaction. It was for the first time 2017 that in order to describe this phase shift, one needed to go beyond homogeneous Newtonian gravity. So up till that time, it was not only Newtonian gravity, but essentially constant acceleration. So that's, I think that is really, really shows how big gap there is between experiments and the aspiration to understand everything that is to know about the foundations of the quantum and general relativistic world and all the concepts that, of course, we will study. But I think that is that is something that can motivate research into the regime where it, theoretically one might think everything is already known, but there might be still new effects lurking that could be useful to help bridge the gap at least a little bit. The second class of such experiments that I find particularly nice are experiments where you trap neutrons in the gravitational potential well above some reflecting surface, so you create a wedge-shaped potential. And again, that's, I guess, maybe nice just for theories because you can get analytical solutions, but you can also do experiments. So I think probably that's this kind of unique situation where you can find it both practical and also describable. Here you have a picture of the setup, this gray aluminum box, and I believe that this part here somewhere, or maybe here, is where the neutrons are propagating to where they equilibrate. And of course, there is a fundamental framework, or at least the one that we currently can put a finger on as the most fundamental from fully completed ones, field theory, quantum field theory in curved spacetime. But that's exactly where, in some sense, the exploration starts, because the natural phenomena that are inherently captured by this framework are typically accessible or show up themselves at high energies. So in terms of bridging the gap between experiments and the theory, this doesn't make it obviously simpler. So there is a different strategy that one can pursue, and that is what I would talk a little bit more about. And so this strategy relies on understanding that we actually do measure relativistic phenomena that are not associated with typical high energy or fast velocities, and this is when we employ clocks to measure time dilation on redshifts. So already in 2010, such experiments with atomic clocks could measure gravitational redshift at the scale of 33 centimeters. So you have these atomic clock setups, which means atoms trapped in some optical potential, and order of 10 centimeter separation between such setups was sufficient to produce enough gravitational redshift between internal energies and therefore frequencies of these clocks to be measurable, and likewise. Moving in some sense, trapping potential for one such clock led to detectable special relativistic time dilation. So this order of 10 meters per second. So this is a human scale. So this is certainly not some high velocity. So let's say after taking a course in special or general relativity, if we ask if 30 centimeters is a relativistic scale in gravitational field, or if this velocity of, say, trotting or maybe fast walking, is it relativistic speed, we would say no, but simply because we are used to very lousy clocks. The answer is yes, of course. We just need a clock that is precise. Can measure time to such and such precision. So essentially, if we had arbitrary precise clock, there would be no regime in which we could apply non-relativistic physics. And since these systems are getting now so precise that you can measure time dilation across millimeter scales, it's worth to explore a little more a theory that can describe such systems that are used in these setups inherently, so atoms that are both described by quantum mechanics, and where we can include directly in the dynamics of these systems the relevant relativistic corrections that could be observed at low energies. And that's exactly the topic of composite particles in the context of general relativity. And so there are, of course, various ways you can start, because we are here only after an effective model. So there will be many different starting points that in the end lead to the same effective theory. I mean, in the end, this is if you only want to recover the lowest order relativistic corrections that come from the redshift type effects. It will be more clear, I guess, as I go. So here are just some examples of starting with something like a bunch of electromagnetically interacting particles, or some composite field in space-time described by some metric. So typically, actually, I mean, all these formulas actually only hold if you have static symmetric metric. And depending on the set of slides, I do mention it or not. So let me say it right now. And so in each of these models, you can take steps to recover the regime where you have one particle sector, where for the field, where you introduce a relative coordinates for the rest center of energy frame, and there is a regime where it approximately can be done in the relative coordinates, and you recover effective description that looks like so, where you essentially have a dispersion relation like you would naturally write down for a relativistic particle, but you have internal energy that essentially presents itself as a rest mass that is given by the operator. So that's exactly the energy of this composite system in its rest frame. And so you can call it M or you can call it H. That's really just the difference in the symbols you like to use. In effective models, like the one would have behind anything like an atom that we'll think of throughout this talk. One should think of this operator is essentially, it's a highly complex system, and it has nuclear energy scales and electronic energy scales, but essentially you will only access very few of these internal energy levels, and in this talk only 2. And so the lower one you can call M, so the ground state of your Hamiltonian, you can call M, and everything else you can define as your internal Hamiltonian, essentially Hamiltonian that drives the dynamics relative to the center of mass. And when you include this split and look at the low energy expansion of this Hamiltonian, you find the fully non-relativistic dynamics of the center of mass, just a non-relativistic particle, some Newtonian potential, and then you find correction terms that couple center of mass and the internal degrees of freedom. And so these are the ones interesting from the point of view of trying to look at the time dilation or redshift effects, because these are exactly those that capture these specific phenomena. Now there are, of course, other terms that if one would like to have just a Taylor expansion order 1/c², but they will only contain center of mass terms. And in the regime, like cold atoms in some trap, one can verify that essentially there is a regime in which you can neglect such terms, where you cannot neglect those that couple the internal and the center of mass. So this becomes really particularly elegant, because if you fold it back, essentially you will find that you effectively obtain a system that looks like a non-relativistic particle with just mass energy included. And so these terms are exactly those that incorporate a redshift or time dilation effect. So phi stands for the gravitational field, and you can easily see if the internal Hamiltonian has some frequency omega. This term gives you gravitational redshift of this internal frequency. And for some semi-classical motion, if you recall P on M to this order will give you velocity, then you get the lowest order correction that comes from the Lorentz factor due to the kinetic motion. Now, in experiments like those with atomic clocks, one of course has to describe, fully in terms of quantum mechanics, the internal degrees of freedom. However, the center of mass is typically considered classically or semi-classically. You consider the atoms are trapped somewhere, you are not giving a full quantized description of both, but that's exactly what will be the interest for this talk. And so Igor already mentioned that if you have some system like this, where you have a particle that has internal states that can evolve in time, you can think of it as a quantum clock. And instead of having two sets of clocks at different heights, for example, you can have one at superposition of height, and then you get, instead of typical interference fringes with just some phase shift that depends on gravity, you get some modulation. And this modulation is an effect that will not be there in a non-relativistic theory with a quantum clock, and of course would not be there if you have a relativistic classical theory. So if you've had classical relativistic particles in the interferometer, well, they will also not show interference fringes. So in that sense, this is an example of an effect that combines both. And there are some prospects for experiments. Now, in the remaining minutes, I'd like to highlight some other incarnations of these composite particles. So far, I built all the intuition around those particles that can be seen as idealized quantum clocks. They can have quantized center of mass and quantized internal states. But because essentially time dilation and mass energy equivalence, they are just two different descriptions of the same physics, these particles inherently are also they have different states associated with different mass, and in that sense they also allow to study equivalence principle and in general theories with quantized mass from this perspective are put on firm footing. You can couple them to some external field, and we heard already today Evan talking about a model that arises from that, where you have a quantized center of mass dynamics. You couple also to the field, so this can be studied in this context. And you can also couple them to some external bath and have a quantum thermometer. In the remaining 3 minutes, probably, perfect, I would like to highlight one aspect that comes kind of from the side, but it turns out of interest to people that are planning to make experiments using, for example, atomic clocks more and more precise. And so to lowest order, obviously, such any trap particle you can describe with some potential. So we'll use to ping pong the pan. This is the ADS of the quantum mechanics, the harmonic oscillator. You will have to watch a talk of Sundborg to understand the reference. So we'll be looking at composite particle subject to gravitational potential and harmonic potential. So this is an exercise essentially. Everything about this can be solved exactly on just a few pages. And so typically when we think of some harmonic trap and the qubit inside, we would think, well, we'll have some states associated with the qubit and some states associated with the trap, and that's it. And while this is very simple, it's actually doesn't give you exactly that picture, and you can very easily see why it's the case when you just formally write down the normal mode operators here. And of course, the fact that you have a spectrum here, I mean, your mass has some spectrum, but if you just recall that the solutions for any trap system essentially depend on the mass, you'll recover that your modes depend on the mass. And what it gives you essentially is, so, well, you can find description of these modes, but probably the more interesting thing is that if you look at the spectrum and the eigenstates, so the eigenstates are correlated, so you don't have a separate tensor product. So the eigenbasis is not tensor product of the eigenbasis. And the energy spectrum acquires some corrections. So interestingly, one of such corrections is known to the quantum clock community, and that's called the time dilation shift. And the interpretation here is if you have an atom with in some thermal state in a trap, It has some kinetic energy, so if it was a classical particle, it would be moving around with some velocity, and there will be some Doppler shift. Now, if this is a thermal state, there is a spread of velocity, so you get some spread in the frequency of your atom. So with this kind of back of the envelope, they can calculate from knowing the temperature of the atom and parameters like mass. They can get the order of this shift. And here, this is something that with even this very simple model, you can just very easily derive. So this is the same effect, and this has been seen, of course, in experiments. Then there is this additional shift. I mean, additional just in a sense that it hasn't been measured yet, but apparently people in this community have been discussing whether or not it should be there. So yeah, at least within this setup, it should be there, a shift that simply comes from the fact that if you have some fixed trap stiffness such that both states see the same potential, then the center of this potential is different for different masses. And this shift then also corresponds to the shift in the spectrum. And there is some absolute minimum to this shift that happens for some very low trap frequencies. I think I'm now at the end of my time, so perhaps I'll just move on to conclusion. I had some bonus topic, but I'll skip it, and I'll just move to my conclusions. I'll move back to the first slide. Some CTC. I have some trouble finding, maybe. In summary, I think we probably don't even need the summary, but I think there is, apart from fundamental questions that I don't want to neglect, I just thought to fill in the niche, but apart from fundamental questions, one can also ask questions about how we can capitalize on the kind of theories that we have been developing to help find some experimentally friendly way to look at the regime beyond the one that has been tested so far. And I think maybe with this I'll end. If there are any questions, I'll be happy to take them. Thank you.
Have some time for a couple of questions if you want.
Yeah, go on. So the effect of gravitational potential in the sense of mass motion, you said that was not relevant for the time dilation?
For the clock experiment. Yes. So this, the tighter is the trap, the smaller this effect is. I think I maybe had a number. I think from memory it would be a shift, like a relative. So this effect would introduce a relative frequency shift at 10 to minus 26. That's not something that can be seen currently, and so whether it's there or not cannot be said. But 10 to minus 19 is something that would be what kind of determines the minimum frequency shift in some of the experiments, like trapped ions.
Is there a qualitative way of seeing why the scales are so different for the two contributions?
Well, so one is essentially okay. In a sense, I think yes, because one. So if you switch off gravity completely, then you have only one, and that comes from special relativity. That comes from the fact that even if I don't have gravity, but I have harmonic oscillator with varying mass, this will give you some additional effects on the spectrum. And then additionally, you have a constant force. And so they are these two different effects. So one is essentially that you just have a effectively interaction because of the kinetic term between internal degree of freedom and the center of mass. And then the other one is an additional force that shifts the equilibrium states.
Yeah. In the cow experiment, so the fluctuations of the phase, would it tell something interesting about, or are these so there is this phase by Newtonian potential, but are there fluctuations around it that are measurable, and would that tell anything about the quantum nature of gravity, like fluctuations in LIGO kind of scenarios, or would it?
Okay.
It's not.
Okay, I can maybe I can address a cow experiment, because maybe that's something where I feel more more confident. I understood the question. So yeah, nominally you could take a neutron. So if you people studied it, like we didn't really start it. So you can take a neutron in I think the most complete description, at least I've seen already in papers probably from 80s or 90s at least, actually from Japanese authors. I think Matsumoto was among them. They would you can study how such an experiment would look when you describe a neutron via Dirac equation in curved spacetime, and you find some additional contributions to the phase. Now, from our perspective, it will be interesting to add some additional external field, so you can use the spin of the neutron, and this can help to give some additional handle and introduce then something more akin to the clock. And with Germain, we look at something like this in the context of these neutrons that are trapped above the table. So there also you can add some additional field and ask, how big the additional relativistic effects would there be? Because to lowest order, even though we have a spin, it gives something similar to the mass effect. I think we need a pretty solid magnetic field. Something like blowing up the laboratory would be kind of just a bit short of, but it just was more to see qualitative. But with the joking aside, if you actually look from the point of view of metrology, Germain found that actually that could be ways to find more precise ways of measuring than just kind of waiting where the neutron comes out, and that's something that could be explored to kind of ask this question. Maybe what exactly one would need to measure, so to see those corrections rather than just doing all the experiments and looking for corrections. There might be different ways to make measurements that would be more sensitive to those effects.
Okay.
Yeah.
So we can thank Magdalena.
Yep. Thank you.
Maybe I just pass.
Yeah.
So yeah, the next speaker is Sri, actually Sreenath, but we call him Sri here. He will talk about the statistical arrow of time and some thermodynamics and some clocks and all the things you work.
Yeah, thanks, Vasileios, and also to all organizers. So I'm going to talk about, so the title here looks slightly different, but basically thermodynamics of quantum measurements, and then interesting applications to clocks and also engines and refrigerators. I'll also talk about arrow of time for quantum measurements in this talk. So here is a brief overview of topics I work on. I'm interested in different scales of quantum systems. In the small quantum systems regime, it's quite interesting because you can use simple qubits and quantum oscillators and continuous measurements to probe different symmetries related to time, for example, time reversal symmetry and time translation symmetry. And in the mesoscopic systems regime, this is where many body quantum effects come into play. You can also have quantum advantages or advantages, especially when it comes to thermodynamics or applications to cooling in the quantum regime. And then also large quantum systems is also interesting test beds for analog gravity of quantum analog analogies to proposed quantum theories of gravity in tabletop experiments, as well as tests of low energy signatures for quantum gravity. So in today's talk, I will focus on the first part mostly, and I'll give a brief introduction. I will talk about arrow of time for quantum measurement process, and also fluctuation theorems which constrain this arrow of time from a thermodynamic viewpoint. And then I will talk about quickly cover three applications of this, which include engines, refrigerators, and clocks. So as you know, equilibrium thermodynamics is classical thermodynamics. It was largely motivated by the need to optimize engines and refrigerators. So for example, you can have different thermal reservoirs coupled, and you can
make use of a temperature gradient to get some work out of the system, and you can characterize the performance of that device with an efficiency. And there are also refrigerators where you do some work to cool down one reservoir relative to another, and then you can have figures of merit like a coefficient of performance. There are also some recent works on thinking that clocks are also thermodynamic systems. Here are some nice references. The idea is that the heart of a clock is an engine which does the necessary work to fuel the ticks of a clock, and therefore the precision and accuracy of the clocks should also be limited by thermodynamic principles. I would largely skip most of the recent developments in this field, and I will go into the quantum regime of thermodynamics of small systems. By small systems, what I mean is that the energy exchanges in the system are of the order of a few kBt, and also the ensemble size that we are describing are small. So we have like 10 or thousands of qubits, or even more single realizations of processes happening at the level of a single qubit. And this is an interesting regime of physics to explore, because fire, as you know, it's one of the oldest inventions of mankind, and these delicate quantum technology platforms are kind of the newest. So we are putting them together, and interesting things are expected to emerge out of this discipline. So so the time reversal symmetry, essentially it's better called the reversal of motion symmetry. So the way to understand this is that if I record a movie of throwing a ball up in the air and play this movie backward, I would not be able to tell by simply watching the movie alone which direction this movie was recorded. And it is evident from this symmetry is evident from the dynamical equations which describe the system. In this limit, the Hamilton's equations of motion, they are time reversal symmetric if I put t going to minus t and p going to minus p in these equations. Similarly, in quantum mechanics, the governing dynamical equation is the Schrodinger equation, and it is also time reversal symmetric if I put t going to minus t and also complex conjugate across the equation. And the observables also change under time reversal in correspondence with their classical counterparts. However, there is this process which is quantum measurement, which seems to break this time reversal symmetry in the strongest sense, in the sense that in textbooks we describe a quantum measurement process as a black box, which is the measurement apparatus interacting with the system of interest. It gives us real numbers as outputs. These are the eigenvalues, and then corresponding to each of these real numbers, we update our knowledge about the quantum system by applying a projector on the initial state of the system. And this projector can have zero eigenvalues, and as a matrix, this is not reversible. So there seems to be some sense of irreversibility in the way we acquire information from a quantum system. We can so the way we kind of try to get around this issue is by considering continuous weak quantum measurements. If you have questions in between, please do stop me. So let's think about measuring a single qubit. And the idea is that the qubit is initially prepared in some arbitrary superposition state, and we want to measure the spin of the qubit. The idea is to couple this qubit to the spin degree of freedom to, let's say, momentum of a wave packet. So what is interesting about coupling to the momentum degree of freedom of a wave packet, this could be an electron or a photon wave packet, is that now the wave packet undergoes displacements conditioned on the spin state of the qubit, because momentum generates translations in the Hilbert space of the wave packet. And then we can look at do a quadrature measurement, measure a quadrature which is complementary to momentum, let's say position of the wave packet, and we get a weak information about the spin state of the qubit that we wanted to probe. And these measurement operators have this Gaussian form because we assume a Gaussian wave packet to start with, and they also satisfies the completeness relation. And one can have a sequence of these realizations. Basically, another photon now comes by and interacts with this system of interest, and we do a quadrature measurement of the second photon, and the third photon comes and we interacts with the system, and then we measure the quadrature of that. So we can get a quantum trajectory, which is a sequence of these states conditioned on the readout that you get at each instant in time. And one can also associate the path probability density that a given trajectory is realized. This I would call the forward probability. And just to contrast this with the conventional picture of strong measurements, the idea is that one could make an analogy to butterflies leaving a nest and going towards two different trees. In the strong measurement limit, you only get the information about which of the two trees the butterflies eventually landed. But what this continuous weak measurement allows us to do is that in addition to the two trees, we can also basically track the route through which the quantum state evolves to an eigenstate. This also introduces the possibility that one can have reversibility at each step, because these measurement operators are Gaussian. We can have the possibility that in the next step, the readout can have the opposite sign of the previous readout, and therefore these two measurements can cancel the effect of each other. So one can, in principle, statistically go back a step in this continuous measurement process, just to say that the butterfly can fly a little back towards the nest with some probability of success. So what this means is that if I make a movie of the qubit state dynamics in the Bloch sphere, I can record this movie, play it forward and backward. Just by watching the movie alone, I would not be able to tell which direction this movie was originally recorded. And it is also evident from the dynamical equations which describe the qubit state subject to continuous measurements. So here R is like the readout variable that you get through from these continuous measurements. So these equations are time reversal symmetric. Basically, if we put t going to minus t and then flip the Bloch sphere coordinates and also flip the Hamiltonian here because you have a spin, so the magnetic field changes sign under time reversal, and then also put r going to minus r, which is the symmetry I was describing, these equations retain the same form. So just by watching the movie, I would not be able to tell which direction the movie is recorded. And in fact, this principle also applies to arbitrary rank 2 weak quantum measurements on a qubit. So instead what we can do is that we can leverage on the access to the measurement record. If we assume that we do not have any prior information regarding which direction the movie was recorded, I can use this measurement record as a soundtrack for the movie to update our knowledge about which direction this movie is recorded. And this gives us a natural discriminator, which is the logarithmic ratio of forward and backward probabilities as a measure, which we will call the arrow of time. Now this is a trajectory dependent quantity. If I repeat the measurement, another realization of the measurement will have a different statistical arrow of time. So I can make probability distribution of this arrow of time, and I can do this for different kind of measurements. For example, the first one is a fluorescence measurement. An atom is emitting a photon and we measure one quadrature of the photon. This is a homodyne detection of fluorescence. There could also be scenarios where an atom is emitting a photon and we measure both quadratures of the photon simultaneously. This would implement a heterodyne detection of fluorescence and the spin measurement that I was describing. So all these processes, we can make probability distributions of this arrow of time. And what you see immediately is that the average of the arrow of time is positive. But then also these distributions are not Gaussian. So the first and second moments alone do not completely characterize the system. So we need to look into relations that constrain the entire probability distribution to acquire all the information encoded in these distributions. And here we use what is known as fluctuation theorems for small classical systems. The idea is that for small classical systems, entropy can be a fluctuating random variable, and thermal fluctuation can assist entropy processes where you don't need to do as much work as compared to the free energy difference to complete the process. Sometimes the thermal fluctuation can assist you in completing a process. Sometimes it can resist completion of a process. But on an average, the entropy is always greater than or equal to 0. And in these cases, what one computes is the average of exponentiated entropy production. So this will be something that looks at all the higher order moments of the probability distribution. And there has been fluctuation theorems derived for small classical systems, which says that this has to be equal to 1 or number between 0 and 1. So with this motivation, which I skipped a little through, we look at the exponentiated average of exponentiated arrow of time, and we get a number between 0 and 1. And these kind of processes are also known in classical thermodynamics of small systems. These are absolutely irreversible processes. An example is free expansion of a single gas particle in a box. So if I have a process where a molecule is constrained on the left-hand side of a box, I can remove the partition and the particle will expand to both sides. It could be found on the left or the right. The backward process would be where I reinsert this partition, and there is only one path that basically you go back to the initial conditions. Because you expand the phase space volume in the forward process, it generates more possibilities, and therefore there is an absolute irreversibility. So if I compute the entropy, everything can be done with equilibrium thermodynamics considerations, compute the free energy for a particle in a box and so on. We find that the average of exponentiated entropy production is between 0 and 1. What this means is that exponential function is a convex function. So then the average of the arrow of time, when you compute, you get a number which is greater than a positive number, as opposed to the scenario where average of arrow of time or entropy is greater than or equal to 0, which is the usual statement of second law of thermodynamics. This is a stronger version of the second law of thermodynamics, which is called absolute irreversibility in classical systems. And in this scenario, what this degree of absolute irreversibility parameter that comes on the right hand side of the fluctuation theorem means is that it computes the degree by which two initially orthogonal states are taken closer and closer as a result of the quantum measurement. As you know, a measurement process can be a many to one mapping process. So this essentially, this degree of absolute irreversibility in the quantum measurement problem reflects the many to one mapping aspect of the quantum measurement, and it constrains this arrow of time that I was talking about using fluctuation theorems puts it in a more thermodynamic framework. And we had looked at some experiments. So the simplest experiments one can think about is Stern-Gerlach type of spin measurement. So you prepare atoms in a given initial spin state and then put them through a magnetic field gradient. And in this case, the position of atoms would reveal weak information about the spin state of the atom, just like the initial distributions that I was showing. And for this case, we can characterize different aspects of the fluctuation theorem by simply looking at the picture that one makes in the end of this experiment, the cloud absorption image. We have also looked at this framework for initially correlated atomic clouds. So we take a Gaussian cloud and then a spherical cloud and then attach different modes of this into different spin degrees of freedom. And one can also extend this fluctuation theorem to compute the absolute irreversibility of quantum measurement in these kind of scenarios. And now I'll come to the final part of my talk. I want to talk about 3 examples where this is useful in the thermodynamic sense. The first one is a feedback controlled engine. The idea is that we have a qubit and we measure the spin state of this along the sigma x axis. So now the measurement kicks it to a higher energy state, which could be either plus or minus eigenstate of or close towards these eigenstates. But then I can extract work from this by applying a feedback which rotates the qubit state back towards the ground state. And then the question is that if the daemon is doing a weak quantum, the experimentalist who is doing this weak measurement is a Maxwell's daemon. The daemon can basically play the game of recording this measurement process and playing it forward and backward, associate an arrow of time for the process. And the interesting question is, how does the arrow of time perceived by the Maxwell's daemon relate to the work that the daemon can extract from the system? And we find that one can in principle write down the work that a daemon can extract in these kind of scenarios is completely determined by the arrow of time, statistical arrow of time that the daemon infers for individual realizations of the measurement process. That's what's shown here. And the other example I want to highlight is the idea of quantum clocks. So the clocks are interesting systems because a perfect clock would break time translational symmetry. And the interesting question here is what are the ways you can get a clock signal out of a system by only consuming thermodynamic resources. So you should not have another clock in the dynamical description of a clock, new clock. So we look at scenarios where we pump the excitations through an irreversible channel, which is a measurement, which can be thought of as a measurement process. So if you have a system continuously under measurement, but then this measurement apparatus is broken in some sense. So the measurement is happening, we are not acquiring any information. So there is no way to undo these effects of measurement, even for weak measurements. And we find that and then monitor the ticks that come out of this two-level system through resonant fluorescence measurements. And what is interesting is that the finite time statistics of ticks coming out of this two-level system can be solved using large deviation principle, and we can compute characterize the quantum nature of these clock ticks and what is the effect of somebody watching the clock tick on the ticking rate of the clock itself. And that is captured by this Mandel's Q parameter. When it is negative, it means that these are sub-Poissonian, they obey a sub-Poissonian statistics, which means that the clocks tick more regularly than a Poissonian clock. And one uses a tilted Lindblad approach to compute the large deviation calculations here. Finally, this is work with Sofia. I would like to highlight one cooling applications of continuous measurement. So one possibility is that if you are familiar with the child in a swing problem, if a child is oscillating in a swing and the child decides to stand up and sit down at twice the frequency of the natural frequency of oscillation of the swing, the child can increase or decrease the amplitude of the swing. And whether you increase or decrease depends on where in the cycle the child decides to stand up and sit down. So the same principle can be applied to quantum systems too. But then the interesting thing is that we need to acquire the phase information of a quantum oscillator. And this requires measuring both quadratures of an oscillator simultaneously. And this introduces fundamental noise limits into the oscillator. So what we find is that we can cool down to below 1 quantum, which would qualify as a good method to reach ground state, because then one can combine it with linear feedback cooling techniques. But there is a fundamental limit which comes from the noise added by the quantum measurements of simultaneous measurement of joint non-commuting observables. With that, I will conclude. It is interesting to think about quantum measurements as a new paradigm where one can think about irreversibility, which can be rectified to produce some useful work or produce ticks of a clock or so on. So there is interesting thermodynamic aspects to this. It also attempts to address interesting questions in relation to the symmetries of time using simple quantum systems, which can be accessed in experiments. For example, in this work, it's using superconducting qubits or ultra-cold atoms. With that, I will conclude. Thanks.
Thank you very much for the interesting talk. Are there some questions?
Yes.
Hi. So there's one part where you use Bayesian stuff, right? The Bayes theorem.
Yes.
So essentially, there the reverse process you need to sort of kind of use Bayesian reproduction to kind of like work backwards.
Yeah. So you would use this kind of principle. So what we derived is that if you have a measurement record, the backward measurement or the process that takes you back is not simply retroduction, which you just usually have just the dagger of the process, but you also multiplied by the time reversal symmetry operator for a qubit, which is I sigma y times complex conjugation. So, but this is the process that would take you back through the same sequence of states back to the initial state.
Okay, so this has nothing to do with the fact that usually if I give you a forward process, the retrieval is not unique, right? Because Pratt's method is one way, but there are many other ways to do it.
Exactly. So what we impose is this symmetry of the dynamical equations. Basically, we want to go back through the same sequence of states back to the initial state.
Any other question? If not, let's
Thanks.
So the next speaker is Germain, and he will talk about single graviton detection.
Thank you, Vasileios. So, today I'm going to be talking about detecting single gravitons with quantum sensing. So, first of all, I'll start talking about what I actually mean by the concept of particle detection in the context of gravitational waves. Then I'll talk about how we can enhance single graviton processes with macroscopic quantum systems to make this kind of particle detection more realistic. Then I'll talk about the concept that I've developed with collaborators, including Sreenath and my supervisor, Igor Pikovski, and another PhD student at Stockholm Institute of Technology, on a gravitational version of the photoelectric effect with a quantum acoustic resonator. And then I'll conclude with some remarks on what this experiment would actually mean for quantum gravity. So when we think of particle detection in say, an electromagnetic context, usually mean some kind of quantized matter system with discrete energy levels, which interacts with some external field and undergoes discrete transitions between those energy levels. And so, for example, in the context of electromagnetic radiation, this would be the detector absorbing a single photon and then undergoing a single transition to the first excited state. So these kind of photon detection processes were really key in the formulation of quantum theory in the early 1900s. For example, the Bohr model, where the atom undergoes transition between its bound states and absorbs and emits single photons, or the photoelectric effect, where instead of a transition to a bound state of the atom, you have a transition to a continuum of excited states, or the free electron with varying kinetic energies. Now, although the modern view of what a detection process is a process where the detector clicks when there's only a single photon input. So going back to the experiments from the 70s and the 80s, where the first experiments on measuring G2 functions were done, since then we've really thought of the concept of detection as being when this transition occurs when a single photon is present. However, the original studies of the photoelectric effect were not single photon input. They were stimulated processes where the wave the detector was interacting with was really of high amplitude, consisting of many, many photons, rather than just one photon. So the question that was set out to answer in this project was, can we observe a detection process, like I was just explaining, for the interaction between gravitational waves and quantum matter? And the conventional answer to this question is no. So Dyson famously did an analysis of whether it's possible to detect a single graviton, and there were two reasons for why he reached the answer no. He was using this more modern concept of detection, where when the detector goes click when there's only a single photon or a single graviton input. And they were only considering these processes for atoms. So looking at the graviton emission and absorption rates for really microscopic quantum systems. However, quantum mechanics is no longer limited to just atoms. We can prepare massive optomechanical systems in mass scales that are much, much larger, orders of magnitude larger than single atoms. So so in our paper, we reached the contradictory answer of yes, and that is the basic concept is that if the gravitational wave can induce quantum jumps between energy levels of a massive quantum acoustic resonator, then that would be a gravitational analog of these photoelectric experiments from the early 1900s. And the key insight behind that is that you do not really need a single graviton input to infer the exchange of single energy quanta between matter and gravitational waves. And that's exactly the same principle on which the photoelectric effect works. So we don't need this modern concept of detection where the detector goes click when there's only a single photon or a single graviton input. If we want a detection in the sense of the early 1900s, which is what the photoelectric effect was, it doesn't matter if the gravitational wave is a coherent state consisting of 10 to the 36 gravitons. We can still infer the exchange of single gravitons between the gravitational wave and quantum matter. So the basic experimental setup we had was or we proposed is a Weber bar, which is literally like a 2-ton bar that was originally proposed by Joseph Weber for detecting gravitational waves. But instead of just a regular gravitational wave detection, which would involve monitoring the average energy, what we propose is a continuous energy measurement, similar to the so Sreenath did the analysis of the continuous energy measurement in this context. So it's nice that I'm following up his talk. But really, if you have a continuous measurement scheme like he was discussing in his talk, reading out the energy levels of this massive resonator, you can really resolve single discrete energy exchanges between the gravitational wave and quantum matter. So now we'll get into how these single graviton processes work for such a massive 2-ton gravitational wave detector. So linearized quantum gravity in low energy radium was first studied by Bronstein in 1935. And so when you go through and quantize the gravitational field perturbations, it results in gravitons in direct analogy to electromagnetism. So Weinberg's calculation was to take this quantized gravitational field and compute the rate at which an atom emits and absorbs gravitons. And when you do that, you get 10 to the minus 40 hertz. So nigh on impossible to detect a single graviton using a single atom. So the two enhancement mechanisms that I kind of touched on before are that we look at massive quantum systems. So quantum mechanics is no longer limited to just atoms. We can prepare massive systems on the order of kilograms even. So the LIGO mirror is a kilogram scale, and it's been prepared close to its quantum ground state. And we look at stimulated emission and absorption. We reject the notion that it's only a detection when there's a single photon input. If it's stimulated, we can still consider it to be a detection of some kind. And so, so the main, as I was kind of discussing before, there's the main experimental protocol we look at is this Weber bar. So the way these Weber bars work is that it's, as I was saying, it's literally like a two-ton. Think of like a massive cylindrical cylinder. And when the gravitational wave comes along transverse in a transverse direction to the longitudinal axis of the Weber bar, it excites oscillations along the longitudinal axis of the Weber bar. So think of these atoms as all being placed along the longitudinal direction of the Weber bar, and the gravitational wave really excites collective oscillations of those atoms. So it produces phonons in the Weber bar. And when you look at the interaction between the gravitational wave and this quantum matter system, the interaction scales with the number of atoms that are collectively oscillating and collectively interacting with the gravitational wave. So you get this enhancement. So you get this enhancement with the number of atoms that make up the Weber bar. So this will really help us bridge from that 10 to the minus 40 hertz from a single atom to something much, much larger. And we find that when you look at spontaneous emission, so that's this Weber bar interacting with the gravitational vacuum, the rate, if you initialized these phonon modes in the n equals 1 Fock state, and then looked at the rate at which gravitons are emitted from, say, the transition is from the n equals 1 Fock state to the ground state, and it would emit a graviton, the rate for that process to occur is 10 to the minus 33 hertz. So already much, much better than the atom, 7 orders of magnitude we've bridged, but we're still a ways away from getting this to something observable. So now we look at stimulated emission rather than interacting with the gravitational field vacuum. We just look at the Weber bar interacting with a coherent state of high amplitude. And for an aluminium bar close to what Weber had designed, and for the gravitational wave amplitude close to what LIGO had detected, you obtain 1 hertz. So the Weber bar and the gravitational wave exchange a single graviton each second. So that really brings this single graviton transition rate to something that we can actually realistically observe in a laboratory experiment. So this calculation I just showed you is Fermi's golden rule. So it's quite a quick and easy calculation to do, but it only applies for a particular situation, namely that when the Weber bar is interacting on resonance for a long duration. So if we want a more realistic model of the interaction, we need to account for the gravitational wave's frequency chirp. So the real detected gravitational waves that we know exist have a chirp in that their strain and frequency changes over time. So we need to account for that in our interaction Hamiltonian. And so what we did is we solved the dynamics to optimize we calculated the parameters that would optimize the absorption probability for a single graviton. Because in principle, the gravitational wave can excite higher energy levels in the mechanical resonator, the n equals 2, the n equals 3, the n equals 4 Fock state. But we really want to isolate this, the probability to measure the n equals 1 Fock state. Because if you measure that process, you can say you've measured that the resonator transition to the n equals 1 Fock state. That means you've measured a process where a single graviton was exchanged between the gravitational wave and the quantum matter system. So calculating the parameters that would be needed, we looked at a number of possible gravitational wave sources. The first 4 columns are for LIGO band gravitational waves. The next 2 are for expected continuous gravitational waves. And the last 2 are from speculative sources in the high frequency range. But our main focus was for these LIGO band gravitational waves. Because if you did a detection in the LIGO band, or if you could get the quantum technology to work in the LIGO band, you will know with 100% certainty that you will get this experiment to work, as in you will be able to do a gravitational version of the photoelectric effect. There's no question of like, oh, will I run this experiment and even see anything, because I don't know if the sources exist. We know with 100% certainty that we will, if you can get the detector to work in this frequency range, you will see a signal. And so that was our main focus. And so zooming into the second column for this neutron star merger that was detected back in 2017, we looked at the parameters that would optimize the probability of absorption for a single graviton. And the required parameters for this absorption rate to be larger than thermal noise is what we looked at, are actually not that unfeasible. So, you only need to detect a mass of 250 kilograms, a Q factor of 10 to the 10. So the Q factor is if you ring up, if you have a single phonon in the bar detector, the Q factor tells you how many oscillations that phonon will undergo before the oscillation dies out. And the environmental temperature, 1 millikelvin, which is not that far off what can be achieved in current laboratory experiments in terms of the temperatures dilution refrigerators can reach. So let's compare this to what has been achieved. So in the last time these massive Weber bars were really in use, in real active use for gravitational wave detection, to the best of my knowledge, was in the 90s, before their funding got abandoned in favour of LIGO interferometers. And there they had a 1.5 ton niobium bar in Australia with a Q factor of 10 to the 8 and a frequency of 700 hertz. So if you look at that, that's compared to the parameters that we need, it's really not that different. And more recently, they achieved the same, or one of the same group achieved Q equals 10 to the 10 at megahertz frequencies. Okay, so that's much higher frequencies, but it's really showing you that these parameters are not really not impossible. However, there's one thing that I'm neglecting to mention, which is that in order to have a direct photoelectric analog, we really need quantum sensing. So we need projective measurements of the bar's energy levels. So this is what hasn't been achieved in a system of that size. So Sreenath simulated the continuous measurement of one of these massive bar detectors, and so initially here you've got the bar detector initialized to its ground state, and then at about the 44-second mark here you've got the incidence of a chirping gravitational wave that closely mimics that neutron star merger that I was showing just before. And the simulation showed that for a bar of around 30 kilograms, you would for the particular measurement strength he was using in that simulation, you would see this collapse to the n=1 Fock state. And this would give a direct gravitophononic analog of the photoelectric effect, or the photoelectric case, where you have these discrete transitions between energy eigenstates of an atom. So what has been achieved in terms of this quantum sensing and being able to measure energy levels of these acoustic systems? And so most recently, to the best of my knowledge, the best that's been achieved is a direct energy measurement of individual levels of microgram mass acoustic resonators. So these are miniature, so they're phonon modes, internal phonon modes of these of the same work of the same principle, as in that they're acoustic oscillations of some bulk material. However, what they've been able to get these projective measurements to work for is only on the order of about microgram masses. So still many orders of magnitude to bridge on the quantum sensing side. So this experiment is not impossible, but it's still challenging. But what would it mean if we actually did it? So the three archetypal signatures of the photoelectric effect that we all remember are the threshold frequency, the independence of the ejected electron energy from the classical field intensity, and the near instantaneous ejection of photoelectrons. So in our gravitophononic setup, we have all these signatures. So we have a threshold frequency, namely that or instead of photoelectrons, gravitophonons only get produced close to resonance, or when the gravitational wave frequency reaches a certain threshold frequency. And you have that when you produce these, when you collapse the system to the n=1 Fock state, you get that the produced gravitophonon energy is independent of the classical gravitational wave field amplitude. And in our case, the timescale for the gravitophonon production is the measurement strength. So that's the time scale for the collapse to occur, which is what the analog of the time scale for photoelectrons to be produced would be. So the caveat here is that, okay, the photoelectric effect was explained by Einstein in 1905 in terms of light quanta, but many, many years later, Lamb and Scully came up with an explanation for the photoelectric effect that did not involve the quantization of the electromagnetic field. And later, I believe later, Jaynes and Cummings came up with the semi-classical model of electromagnetic radiation interacting with an atom that we all study in undergraduate physics. And that model can account for transitions in atoms and the photoelectric effect without quantizing the electromagnetic field. So what does this mean for the quantization of gravity? So, however, the caveat there is that these semi-classical models must violate energy conservation, in that if you have a discrete transition on the matter side, if energy is conserved, that means that there must also be a discrete h bar omega transition on the field side as well. Of course, you can have a non-energy conserving theory where you still maintain a description of the gravitational wave as a classical continuous field, that satisfies the Einstein equations, or in the electromagnetic case, a classical continuous field that satisfies the Maxwell equations. But in order to account for the photoelectric observations, that if you maintain that description, you have to give up energy conservation to explain the result of this experiment. So therefore, if you make the assumption that energy is conserved, the experiment is inconsistent with the gravitational field treated as a classical continuous wave that solves the linearized Einstein equations. So if you make the assumption of energy conservation, you have that the experiment provides some weak evidence for the existence of gravitons. So to summarize, the basic protocol is presented in the paper is that you have some compact binary in spiral. So two neutron stars merging or two black holes merging that emit gravitational waves. Then you have stimulated single graviton absorption in the bar detector at Earth. And at the same time, you're continuously monitoring the energy levels of the bar detector. And you see if a gravitational wave is present, you'll see a discrete click to the n equals 1 Fock state. And then if you correlate that detection event with an absorption, with a detection event at LIGO, then you can have a high confidence that that click you saw in the detector was due to the absorption of one single graviton. So to conclude, single gravitons can be detected in the same sense as in the early 1900s with the Bohr model and the photoelectric effect. This can be achieved with not that unrealistic parameters. And it doesn't prove unambiguously that gravitational field is quantum, but serves as a test of the quantum nature of the field to the exact same extent as the photoelectric experiment of the early 1900s. And this is a subtle point because there are also arguments that to really prove the existence of photons, you need G2 measurements, negative Mendel-Q parameters. I mean, I would say that does, yes, it provides stronger evidence for the existence of photons, or in this case, the existence of gravitons. But it's more like that does not take away from the fact that the photoelectric effect still provides weak evidence for the existence of gravitons, or the photoelectric effect provides weak evidence from the existence of photons. And with that, I'll thank my collaborators, Sreenath K, who is here in the audience, Thomas Beitel, who is a PhD student at Stevens Institute of Technology, and my supervisor on this project, Igor Pikovski. And yeah, thank you.
Thank you very much. Very, very interesting. Any questions? Yeah?
Yeah, thank you for the talk. Very exciting development. Can you comment a bit more about the second point of the analogy, that the energy of the phonon is independent from the amplitude of the gravitational wave?
Yeah. Because
you are projecting on a specific gravitational number, right? Is there any chance that you were exciting phonons of different energies as well?
Yeah. So you could just as well. There is some probability. It's a harmonic. The matter system is a harmonic oscillator. So unlike the atom, there is some probability that you will excite to the n equals 2 or the n equals 3 Fock state. But in that case, you've still got, instead of one single gravitophonon, you've got 2 or 3 gravitophonons. The sum of their energies is still independent from the gravitational wave amplitude. Yeah.
So the probability of, but isn't this kind of tautological because you're looking at that phonon specifically, so of course it's going to have that frequency.
Sorry, not sure.
Like you're looking at a specific phonon, so of course it's going to have that frequency.
Right, as in like the matter can only absorb radiation at that frequency. Yeah, sure. Yeah.
The electrons could have gone with different energies out.
Yeah. Yeah, I mean, one thing you could, like an alternative way to do that, this experiment that would get around that is if you had multiple different detectors of different frequencies, and then if you you only saw a transition in one which matched the gravitational wave amplitude, then you could mimic something like that, mimic a continuum like that. Yeah.
So I vaguely forgot about the story of the Dyser's paper, right? But one of the arguments is actually just based on the fact that any astrophysical sources produces way more neutrinos than gravitons. So do you remember how this argument would have killed that one or two?
So here it's because the gravitational wave signal, well, the signal we haven't calculated what the cross section is for this bar detector with the neutrinos, but I naively would expect that the cross section for interaction with a LIGO band gravitational wave would be much larger because yeah.
Okay, yeah, because I remember the argument wasn't exactly by the single graviton detection stuff, but okay.
Yeah. I think the difference there is that they weren't thinking about the these gravitational wave signals from black hole binary mergers. Yeah.
Any other question?
So basically this relies on the fact that for phonons, the energy levels are very, very small as compared to photons, say.
Yes, yeah.
So you can excite phonon energy. Okay. So can you differentiate between like 3 level 1 phonons or 1 phonon with 3 levels of energy?
One phonon with 3 levels. So I mean, if you excite to the n equals 3 Fock state in a harmonic oscillator, that would be you've produced 3 phonons in the harmonic oscillator.
So they are equivalent to the state.
Yeah.
So we have acoustic modes, which are collective modes of position displacements of each of these lattice vibrations, and then basically the sound velocity is what determines the spacing. Yeah, it's not right.
Cool.
I meant like it's like 3 times. It's not 3 times the frequency.
It will be the 3 times frequency, but you have different modes that you can isolate. So
Yeah.
One that L equal to 1, 3, 5 go up to n plus 1. Those are different acoustic modes with frequencies which goes like L Vs 5 over.
Yeah, right. I think that's a good point to distinguish that there's different modes you can excite, and then number of phonons produced in each mode is a
Let's thank Germain again.
Yeah, my laptop. Do you guys mind to have the doors open? Even if it's noisy, it's better than actually the stuff there. You're gonna have to use the USB-C.
have the pleasure to have Guilherme here. He will talk about gravity, and I'm curious to hear why gravity is weird.
Okay, so thanks for the invitation. I've been struggling during the week to know how to approach this talk, given it's like the last talk on a Friday evening around 7 p.m. And I thought the best would be to first acknowledge that gravity has been beating me up twice as much recently, because I rock climb, but I'm also getting older. So I thought it would be a good chance to actually bully gravity a little bit and remind us of why gravity seems to be so different than other interactions and other quantum fields. As I said, let me start by acknowledging that it is quite hard to be giving a last talk during a long day. So hopefully, after reading this paper during this week about why people nod off during talks, I probably learned a little bit of how to avoid losing my audience. But anyways, so before I start, I'd like to acknowledge that pretty much all the things I'm discussing here, they came about within this collaboration that we started roughly a year ago. We are 7 different researchers spread in Europe, also Eugenia, she's in the States. And throughout the year, we've been meeting every week or so to actually discuss papers on the foundations of quantum mechanics and gravity. And after more or less of a year of reading those papers and thinking considerably about the nature of gravity, today I'd like to briefly step back and have a more philosophy of physics kind of style talk where we're going to analyze closely where gravity seems to be so different, and perhaps like using that to guide us into the future when we try to talk about quantum gravity and relativistic quantum information. So here I have a brief summary of the main points that I'm going to cover. We're going to see that there are 2 different kinds of universality that gravity introduces or presents to us that we have to bear in mind. Gravity also introduces a direct notion of operational measurement limitation, which leads to the idea that we don't have no local gauge invariance observables in quantum gravity. And we're going to also revisit that later in the context of how do we even talk about quantum gravitational subsystems. And finally, in the middle of the talk, I'm going to also briefly mention the holographic principle and the kind of conclusions that some people have been trying to derive by the fact that actually we have this particular scaling between area and entropy in gravitational systems. Okay, so let's go into it. So the first one, everyone here learns even in high school to some extent. We know that gravity is universal in scope. It seems to affect pretty much everything that there is out there in the universe. But not only that, we also learned that gravity actually has a universal strength, which in our modern theories is implemented through a minimal coupling with all the other possible quantum classical fields. And the physical picture comes about through the equivalence principle, as you know. Now the question is this singular to gravity or not? And this has been already observed many years ago by Feynman, that actually there are other situations in which we seem to have an universal kind of interaction. So in Feynman lectures, you find Feynman saying that the fact that universal attraction might remind us of the situation in molecular physics. We know that all molecules attract one another by a force which at long distances, and so let's keep that in mind for later, goes like 1 over r to the power of 6. These we understand in terms of dipole moments, which are induced by fluctuations in the charge distribution of molecules, and so on and so forth. And of course, then he relates that, or he speculates that maybe what happens in gravity, that we have this attraction which is also universal, could be due to similar fluctuation in something. We just don't quite know that yet. So out of this slide here, let's remind, we have a kind of universality that appears in molecular physics at long distances. Okay, let's move on. There's another thing which is peculiar about gravity. As we know, we seem to live mostly across the visible spectrum. And as we've been discussing throughout the day, if you actually want to analyze smaller and smaller subsystems, you have to increase the frequency of your probe. But we know that in principle, before gravity, we could do that all the way to the smallest possible scales without any particular limit. But as soon as we have gravity on, we know that once you have the energy being too high, at some point you're going to reach a barrier in which you don't have any more operationally access to the smallest scales in space-time. So from an operational point of view, it already seems that space-time cannot quite be fundamental, at least in the sense that we won't ever be able to observe what's beyond the Planck scale, either in time or in space. Okay, so now for us to continue our journey, let's forget a little bit about our weirdo, gravity, and remind us about the normal kids, the other quantum fields that we have in nature. When we do quantum mechanics, in principle, there are two infinities that we tacitly assume, even though in practice we cannot do anything about them. Well, the first one is that because quantum mechanics seems to be intrinsically probabilistic, in principle, to derive probability distributions, you'd have to repeat experiments an infinite amount of time. Of course, we don't do that. And so intrinsic to any measurement or any distribution in quantum mechanics, there is some uncertainty around the accuracy of our probability distributions, which scales roughly as 1 over square root of the size of the system, the quantum system. There's another kind of infinity, which has to do with the fact that in principle, if I want to measure anything with apparatus, and I want to use apparatus as a recorder for that information, for every decimal case of your G factor of your electron, for instance, you need to have another factor in Hilbert space to record that information. And of course, we do not have that. And so in principle, actually, there is another scaling, another intrinsic error to any measure, which scales as e to the minus dimensionality of the Hilbert system of the apparatus. And in general, of course, we can ignore that, in particular because this error is way bigger than the second one. So as I said, those two things are always there, tacitly, but in practice, it doesn't quite matter. Because we know that within the formalism of quantum mechanics, without gravity, in principle, you could keep pushing and creating systems which are always bigger and keep repeating the experiments. Okay, let's bring gravity on again. Well, there is a problem here, especially with the second kind of infinity that wasn't so relevant in quantum mechanics without gravity. Because as soon as we try to make our apparatus bigger and bigger, to try to make a precise measurement, a sharp measurement, at some point, again, we reach a limit in which our whole lab would collapse to a black hole. And in fact, we know how to measure the entropy of a black hole, and so we know that that error that appeared there as e to the minus n, if in fact we were to arrive at our lab almost at the size of the black hole, that error actually scales with e to the minus a over g, where a is the size of the black hole. And so from that very heuristical point of view, we already kind of like have a feeling of why there is no precise observable, sharp observables that can be associated with any measurement whenever gravity is actually on. Well, unless we can do something else. Well, imagine that instead, as we try to make our sharp measurement of whatever quantum mechanical with gravity phenomenon, we keep increasing the size of the lab, but like throwing the lab all the way to infinity. So we never really reach the density in which a black hole would be formed. But you can imagine what's going to happen now, right? You have to keep increasing the size, and you have to keep expanding the size of your lab, expanding it all the way to the boundary of your space-time, to infinity. And so in principle, now we also understand why there is no notion of local sharp observable that can be associated with any gravitational quantum mechanical measurement. And so really, at the end of the day, we kind of like understand that the only sharp observables in any theory of quantum gravity should be the ones that are going to be recovered at the boundary, not the ones that are going to be defined locally. And to some extent, kind of like anticipating maybe all the problems with quantum gravity, this is exactly what the program of matrix theory and scattering theory is actually doing. All the observables in scatterings are defined asymptotically in the infinity. And then, of course, the question is, can we then rely on this quantum field theory approach where we're based in matrix ideas to actually account for gravity? And we're going to come back to that towards the end of the talk. Let's again go back to our normal quantum fields, our normal kids. And we see some very peculiar things that were found out already by Sreenath K in 93. Which is the fact that whenever you think about holography, you usually think about gravity, but actually that has been present in normal quantum mechanics and quantum field theory way before we start talking about the holographic principle. And here the idea has to do with the fact that if you go and compute the von Neumann entropy of quantum fields associated with any compact region of space-time, we do observe that there is a scaling of the entropy with the area of your compact surface. And this is like pretty much actually universal and also independent of the state, because when we zoom in, any state looks anyways as a ground state, and the calculation was done for the ground state. And so the picture that people usually have is that actually you have an infinite amount of modes inside the region and outside, which are entangled anyways, and they share the boundary of it. And so that's why the scaling would be naturally coming with the boundary of all the UV modes that are coming across the two sides of your compact space. As I said, let's bear in mind that this was proved to be the case for the ground state. And this, again, is not about gravity, right? And so we have this scaling law, and the finite part scales with the area. Of course, this is already in stark contrast to what we know about classical thermodynamics, where the entropy of any region can scale with the volume, and it can go all the way to infinity. You just keep exciting the states inside that region all the way as much as you want. All right, so now let's again oppose this to what happens in gravity. Well, in gravity, we have something called the holographic principle, which upper bounds the amount of entropy that you can contain inside any particular compact region of space-time. And in particular, this is the formulation in which you write the holographic principle, or the bound for the entropy, by using light sheets which are shoot out of your compact surface. And so this is actually a covariant way of writing this bound, even though initially people were relying on a spatial hypersurface and a non-convariant description of the relationship between the entropy and the bound. This is mostly work by Bosso. Now, remember for Sreenath K and quantum mechanics, that calculation was for the ground state. But black holes are not quite ground state. In fact, we know that from the generalized second law of thermodynamics, if you do have a black hole associated with a compact region of space-time, it has to be the highest entropic state associated with that region. And in fact, I mean, the black holes are going to be saturating what we call the Bekenstein bound. And usually the bound, of course, can be unlimited, but for the black hole in particular, because of connection between the characteristic length of the black hole and the energy, that relation is saturated at a finite entropy. And now if you think that there is a quantum description of the black hole, because it is a system which has the maximum amount of entropy, quantum mechanically, you would see that the dimensionality of the Hilbert space associated with that particular compact region of space-time is going to scale with the entropy. But we know and we just agree that the entropy associated with that particular region is actually finite. And so you'd infer from that the dimensionality of the Hilbert space associated with that space-time region has to be finite. And so you'd be led to believe that whatever quantum mechanical description we're going to associate with that space-time region, it quite cannot be a QFT. Because for a QFT, for any quantum field, for any mode of a quantum field, we have basically a harmonic oscillator, which has a Hilbert space which is infinite dimensional, even if you have IR and UV cutoffs. And so that seems to be quite a stark conclusion. And of course, we can talk about that later, if this follows or not. But this is an argument that was proposed by Bau, Caron, and Sein a few years ago. Okay, there is another thing about the holographic principle that has been used in the past few years, and that comes in this paper by Jacobson in 2015, where by postulating that actually for any causal diamond in your spacetime, that the change in entanglement entropy of this causal diamond can be divided in the IR and UV sector, and the UV sector is what he's going to associate with the geometry, and is going to be scaling with our holographic scaling, he was able to rederive Einstein's equation. Now, what's peculiar about that is the fact that we have now our scaling here, and this is a universal, in the sense that it was fundamental for his derivation of Einstein's equation that this scaling would be a constant, which is not the case if you go back to this paper by Sreenath K. When you compute for quantum mechanical theories, you see that actually the scaling depends not only on the size of the region, but also the energy in which we're considering the system to be embedded in. And so you see that the universality of gravity here seems to be quite different to the universality presented in normal quantum fields when you compute the entanglement entropy for them. And again, for Sreenath K, the calculation was in the ground state, and here we're imposing this for the EUV part of the theory. So it's the EUV that's being universal, which is quite peculiar. Now we go back again to the our normal kids and our quantum fields. And there is one thing that somehow is always lurking in, especially throughout the whole day in all the talks that we have given so far, which is how do we even talk about quantum mechanical systems, subsystems, in particular in the context where gravity is turned on. Quite typically, to talk about a notion of subsystem in which we think that there is a Hilbert space which seems to be localized in some region of space-time, in quantum mechanics that's somehow quite trivial, as long as you have an algebra of observables which is given by the bound operators that can act in a Hilbert space. And this algebra is typically called a type 1 von Neumann algebra, which in the canonical examples that we can have in mind is whenever you have a separable Hilbert space. Then we have a very well-defined notion of subsystem. And that's why we go about writing tensor factors, so on and so forth, when you do normal quantum mechanics. Do we have anything like that in quantum field theory? Well, not quite. In fact, in quantum field theory, to have a notion of subsystem, which here we're going to represent it or instantiated by thinking that whatever measurements and state preparations that we want to have in our labs, they can be carried out independently. You need to rely on two different properties. One is our microcausality, Einstein separability, that in whatever part of the different subsystems we can act over operators which commute among themselves if the systems are space-like. And there is also the property of the split property that I won't go into details of, but my point is going to be to show that even though this works in normal QFT, and we can actually implement or recover those two properties or consistently impose them, for gravity there is debate if the split property is valid, but I won't even go there. I'm going to show that already the first property becomes an issue when we want to talk about quantum gravitational systems. So let's understand what's going on. To understand, let's just look to QED cup with a scalar field. So it's very simple. We can write our Lagrangian. We know that this Lagrangian is locally gauge invariant as long as the gauge field and our scalar field transform in that particular way. And that's pretty good. Of course, then we can impose that for space-like regions, our scalar observables, they commute. But now we have an issue, because we have a gauge symmetry or a gauge transformation of the scalar field in our theory. So even though this can be true, this is not gauge invariant. And so the question is, can we find a gauge invariant observable associated with the scalar field such that it's going to be also local in the sense that's going to satisfy some relationship like that? And in fact, there is a way, and those are called rest operators. And you can, for instance, for this particular theory, you can write down this operator, which pretty much you can think of this whole integration here as if you have now one charged phi particle here and another phi particle here with the opposite charge, and connecting them both, you have a string of this U1 field, if you wish. And so once you do that, you can show that this operator, as long as x and y and z and w are defined in two different operators which are space-like, then they're going to commute as well, and you have local gauge invariant observables. So that's good. And this can be done for all the fields that we know in QFT. But what about our weird kiddo, gravity? So let's try the same with gravity. Let's write a normal scalar field coupled with gravity. Once again, now gravity at the linear level has some gauge symmetry. Let's consider only linear diffs. We have our symmetry here. Our scalar field also transforms. Here already canonically normalized our metric perturbation. Once again, I can impose my scalar field to be commuting at space-like regions. But once again, we have the problem that that's going to be not gauge invariant. Can we recover something that's going to be gauge invariant and satisfies the relationship? Well, it turns out that you cannot. You can actually find gauge invariant dress operators. But once you do that, and basically what you do, you have this particular way of transforming your operator and dressing it with this particular function of the metric over there. Once you do that, and you can, there are many examples and many prescriptions to do that, you can arrive at a gauge invariant operator, but that won't satisfy anymore the notion of microcausality. And so that's very concerning.
What's the main reason for that?
Sorry?
What is the main reason why?
Maybe we can come back to that at the end for the questions. But we have this issue. And again, this was our prescription to talk about subsystems. to talk about experiments, to go into the lab and defining, I have a system A and I have a system B there. And here, this is breaking apart completely, even for the level of linear diffs. So basically, we have our algebraic approach is obstructed in gravity. Because as I said, this dress operator, even though it's gauge invariant, it won't commute with itself in space-like regions. And intuitively, the reason why this is happening really has to do with the fact that in gravity, we don't have positive and negative charges. So you cannot really screen off your gravitational field. And basically, the main difference between this integration and the previous one is that this goes all the way to infinity, while the previous one was actually contained in an extended compact region in space-time. And fundamental to the argument was that even though I wrote Einstein and Hilbert, the only symmetry that I relied on was linear diff. So it doesn't matter really what kind of gravitational theory you're talking about. As long as you have linear diffs as your gauge symmetry, you're going to run into this kind of problem. So basically concluding my talk, now what? And that's I'm here to pose this for you. I would say that perhaps there are hints here on this kind of understanding to update our directions in relativistic quantum information and the kind of things or problems that we should maybe be trying to address and think of. I think there are direct implications for the understanding interpretation of GIE experiments and the whole notion of not only relying on the fact that you can write down subsystems in quantum gravitational experiments that are separated, but even stronger, to write down a cat for our gravitational systems. I'm not sure to which extent everything that I argued here so far would allow you to even consider that. Just want to observe that back to the argument about holography and the fact that we shouldn't think of gravity as a QFT. If everything is locally finite dimensional, in principle, all those problems go away. And so maybe one opportunity is to try to develop and think of gravitational phenomena in quantum mechanics representing a finite-dimensional Hilbert space. Just want to highlight that Feynman's universality appear on the IR, while gravity a la Jacobson appear in the UV. And similarly, Sreenath's calculation is for the ground state for the holographic relationship, while for gravity is for the maximally entropic state for a compact region spacetime. So it seems that there is this opposite happening between the normal quantum fields and gravity. What is that trying to tell us? And maybe all those things are hinting towards something which might be a strong departure from our classic intuition about spacetime. I ran out of time, so I apologize for that. But basically, the message that I would say is that perhaps we should really try to knit our spacetime by really trying to recover that from only quantum mechanics and not having spacetime as a fundamental entity in our ontology anymore. And I stop here. Thank you.
Thank you very much, Guy.
Thank you.
Do we have questions?
Okay, so thanks for a very nice talk. I'm going to say some kind of bullshit now, but maybe on the last slide. So the point on the UV versus IR, right?
Yeah.
Is there any indication that in gravity you might expect something like UV-IR mixing kind of thing? Because in condensed matter even, like sometimes when you have this kind of mixing, you end up with a non-standard QFT, which is like very weird, like photons, right? And I don't know.
Yeah. I don't have much to say about it, but the fact that I would imagine that there is some sort of mixing, but even the mixing, when you think about, it comes from like this idea of like having an EFT where you decompose everything in terms of modes and stuff like that. And if gravity is actually not even a QFT, I guess everything like just like falls apart somehow. It could be that the very reason why there is a mixing is coming from the fact that the underlying framework is not actually a QFT. But I guess those are open questions, right? And those are the big questions, so I don't know. I guess you were the chair.
So you were mentioning this entropy of the compact region, the number of states scaling is e raised to entropy. So you have, so that is like a microcanonical ensemble. Like all these states are like almost same energy.
Well, of course I didn't discuss that extensively, right? No, but like here they would really be thinking that the black hole is actually coming from some quantum state, which is spread across space-time, and then you are now tracing everything out from the black hole And that's why you have this maximally mixed state, which is actually composed in the black hole. And that's what allows you to write down then the dimensionality of the Hilbert space equals to the exponential of the entropy, which is questionable. Some people wouldn't like that argument, for instance, for sure.
I have many questions maybe I ask one or two. So if you have a set of interacting harmonic oscillators, the entropy is not infinite, even though the Hilbert space is infinite.
Well, if you have just two harmonic oscillators.
Or a number of them interacting, the entropy is decided, of course, by the total energy of the system.
Yeah.
So if you see that the black hole entropy is finite,
right,
it does not mean that your Hilbert space is finite dimensional.
Yeah, but I think, right, but the difference is for right. Yeah, it goes on the assumption here that, because for the case that you're saying, like, you could actually increase the entropy all the way to infinity if you keep exciting more and more states.
Yeah.
Which for the case of the black hole, in principle, that is already your maximum entropic state.
You can make your black hole infinitely large.
Yeah, no, but this is for, I was keeping like the region fixed the whole time for the argument.
Yeah, so for a given black hole, the mass of the black hole gives you the energy. So having the energy of the system fixed, your entropy has a maximum. Which would also be the case for harmonic oscillators. If the energy is fixed, you have a maximum entropy. But if you increase entropy, only that. So if you need to increase the energy in order to sample the infinite number of states in the Hilbert space.
I guess the difference that for a harmonic oscillator, you don't have the relationship that the energy is or has anything to do with the size of your system.
Sure. Yeah.
And that's why you can actually take the Bekenstein bound and push all the way to infinity, right? That's another peculiar aspect of, I guess, a black hole in general. Exactly.
The second thing was about this, the Wilson line. So basically, the Wilson line comes from the geodetic equation.
This Wilson line here, when we were like writing down the dress operators.
Any Wilson line, because basically you say for electromagnetism, it's the covariant constancy that gives you the equation for the Wilson line. So in principle, for gravity, also you can write a Wilson line, which is e to the power of the Christoffel correction. And in the linearized theory, you can actually check that that transforms in the correct way like a Wilson line.
Okay.
So why is that not enough? So the one that you quote here from
Giddings.
Giddings, exactly. So so people who do this thing of what's called this BMS symmetries, infrared. The connection between BMS symmetries and infrared divergences, etc. So they use gravitational Wilson lines in the linearized theory, which is essentially e to the power of the Christoffel connection. It doesn't look like the one here, but that apparently seems to work.
Yeah, so Giddings, on his paper, he goes over different prescriptions, actually, of how to dress the operators. And as far as I have seen on his paper, at least, the claim is that there are no way of dressing the operators such that you can have a locally gauge invariance. And that's it. And I think that's like one of the motivations of why people talk about all the different operators on the boundary, like so it's like edge modes, for instance, or like the fact that when you talk about the black hole, somehow all the things are defined on the boundary asymptotically flat. But to be honest, I'm not an expert on this at all, and so there probably are other things or proposals that maybe might overcome that. But yeah, so this was sort of like a double down on this heuristic idea that if you were to actually have any sharp measurement in a quantum gravitational system, you just cannot. Somehow there is this idea that you have to push things to the boundary.
So then you give this example of the detector, you make the
Exactly.
detector which is larger and larger to avoid collapsing into a black hole. But the statement is that the amount of matter in the universe, if you compare that to the Hubble radius or whatever, it seems to exceed the black hole collapse limit, isn't it?
Yeah.
The universe should have been a black hole.
Oh no, I don't think so.
That's the statement.
No, for sure.
Check it myself.
No, I don't. No, that's for sure not. I mean, the average energy density is quite low. I mean, we're very far removed from the Planck scale, right? Yeah.
This is very common. I don't know if anybody else has heard this. I've not checked it myself. But
it seems the amount of material whole observable radius is compatible with us being
exactly. Yes.
No, that as someone who does cosmology, that doesn't make any sense.
Okay. And the final thing about sharpness of gravity.
Right.
I think the most compelling statement about that is that there is no gravitational field for a point particle.
Mm.
You can write a point particle in your action, study its motion under gravity, but if you take that point particle as a source and try to find a gravitational field around it, there is no solution.
Which, I mean, sure. Yeah. I mean, that's the fact that gravity is not normalizable as well, right? So.
Completely classically.
Yeah.
Even in classical theory, there is no solution for the gravitational field of a point particle.
Right. Yeah. But that's also for electric, for like, you reach a singularity also for computing the electric field for a particle.
But that's okay.
No, but
you get an electric field that makes sense pretty well actually.
Mm.
In the sense that it's a singularity, but if you put it in the equation of motion, you solve your equation of motion.
Right.
You have a Laplacian square acting on a potential equal to a delta function.
Right.
That's your equation. You get a solution for that equation.
Mm-hmm.
In gravity, you don't get a solution for the equation.
By gravity, you mean GR, not newtons, right? Otherwise, it would be the same. Okay.
GR.
Sure.
For Newtonian, you can.
Yeah. Sure.
So what does point shockwave work?
A point?
Like there are gravitational solutions for like delta shockwaves, right?
Shockwave probably yes, but not a point particle. Yeah. If you take a stationary point particle,
like really tiny, like point like.
Exactly. So where you have your matter density is a delta function, the particle is at rest. In that case, you try to solve it. There is no solution for that.
Let's thank.
Thank you.
We can share it with. I can be interviewed.
Ah, yeah. So now it's the time for the career development talk. Magdalena will talk about career opportunities here in Stockholm.
Thank you. It's already difficult first time, so. All right, I guess it's self-explanatory. I'll go through some options that were identified in consultation with colleagues that have been here for a little longer, so hopefully we didn't miss anything obvious. But clearly, if we did, and there will be some further suggestion of things to include in this, that's nothing lost, because the organizers have actually added to the Indico page of the Stockholm event a summary of this information with all the links, and so that can be further expanded as need be. I guess I should go to the presenter mode. Oh no, it works. Okay, he just said something weird is here. Okay. Probably. Okay, perfect. Yes, so we're talking about career opportunities in Stockholm, in Sweden. Since we are a global RQI, I learned that one has to put things in context. So Europe starts to be divided a little bit into smaller units. So that's where we will focus. And zooming even more, physics in Stockholm, I guess to my knowledge, happens mostly by large here at Albano. So in particular,
in the building where we are meeting here today, and one connected to it via a bridge. So they form here the star you can see marked as Albano. So this is part of the university campus. So we are at N in Nordita, and F is the physicum. Actually, it's more than physicum. So this is just to give a little bit of background, because part of the motivation, I guess, for these development talks is that people that are not currently at the place can understand a little bit how this place works. So there will be just this very brief section about how things are here organized, which I think is also somewhat different and interesting. There is the center called the Albanova, and this is a center for physics, astronomy, and biotechnology. And it's a joint initiative of Stockholm University and the Rolling Institute of Technology, KTH. So that's quite unusual from my prior perspective. You would have university and technical university completely separate, and the closer they are, the bigger the competition between them and the bigger the barriers to do things jointly. So this is, it's really interesting that there is a shared space and shared events or shared institutes. So the building houses Department of Physics, so that's where I'm based. Various departments also from KTH, Department of Astronomy from the university. Also Nordita is part of this. So the institute that has been mentioned already earlier, and it's also a joint venture between the two. And Oskar Klein Center. So this is a center for cosmology and astroparticle physics. Also part of this, all these joint projects. So I'll go right away to some overview of PhD studies or opportunities. Again, focusing mostly on things through the lens of the university and Nordita. So in general, PhD, and I think this is common for all Sweden, is 4 years. And one is typically employed. This means, unless there is a very particular reason you do not want to be employed, you will be employed. So it's so that somebody will decide. That's and then the salary depends on your institution. Here we've only put the median because there is increase as you go through your study. So as you hit 50% of your requirements, you get an increase. And then if you hit 80% of the requirements, there is another increase. So you start with something like 28,000, I think, per month, and then you go up. So Physicum doesn't have departmental or university scholarships. I see Fabio is this, I think this is still current. There used to be some kind of shared funding in the past, but my understanding is it's probably not clear if it's ever going to be back. So essentially the positions would be, the PhD positions would be opened via individual group funding. So people will apply for grants and then they will open PhD positions. And now when it comes to action points, so this means if you are interested in PhD opportunities here at Stockholm, essentially you have to look for job ads that pop up either on Physicum website. They are usually published on the major typical lists for open academic positions. So that's how you may learn. Well, this also means that you may anyway inquire at supervisors groups that you are interested in joining for PhD, because there might be things coming up on the horizon, or people might not be sure if they want to really get someone, or maybe not, if they will get someone reasonable or interested in the same topic as they are. So that can really lead to a position being opened once it's clear that there is a suitable candidate. So that's something you can one can explore. Yeah.
There are departmental positions, but they are awarded through groups.
Well, I was talking with, I think it was Jan actually, and he said that at the moment there is no funding for this.
Earlier, there were open positions, 2 open positions where you students join and then they can decide which group they want to work with. But then there are non-open positions, which is like various groups get 1 or 2 positions depending on how many students they have graduated, etc. For that, there is money.
Okay. So what would be the order of magnitude per group member per decade? I don't know.
Depends on the size of the group.
Okay.
Exactly, yes. And
But so there would be some very low.
It's
Okay.
a low number, yes. But it could be of the order of 1 position per year or something like that.
But for a whole division.
For the whole division.
Okay, so that would be some 10 groups.
Yeah. So then
okay.
they have to decide how they want to.
Who gets?
Who gets it exactly?
Yeah, I see. So if things are cycled, then yeah, once per number of years that equals to the number of groups in your division, you might get a slot. Okay, maybe that's why you answered essential. Practically, there is no funding. I'm saying Jan, by which I mean our head of department, just to make it clear. So Nordita doesn't have a PhD kind of independent positions as such. But there is a very interesting program of visiting PhD scholarships that I think it's really worth mentioning. So if you are already on a PhD and would like to spend some time working with anyone from Nordita, twice per year there is a call. There is quite minimal application where you need to first contact your prospective collaborator, the local supervisor, to see if they're interested, if they can be here where you want to come, if they want to work with you. Then you write a little proposal and get some motivation letter, both from your contact person at Nordita and from your normal PhD supervisor. So typically these calls are, these stays are expected, or the funding is expected to cover a few months, but if you have some additional funding, of course, there is no reason to extend, so there is quite some flexibility. Moving on to postdoctoral opportunities. Again, things are quite fixed, so currently at Physicum, the postdoctoral positions are essentially 2-year duration, could be extended by 1 year. I guess depending on the circumstances of the dynamics. So that's not something decided by the university, but between a postdoc and the supervisor. Well, of course, for these opportunities, obviously, people that have funding, they open these positions. So again, one needs to monitor the calls. Now, it's important to check for the cutoff times past PhD, because these positions are typically for relatively junior people joining. So yeah, that's just something to have a close look before before one prepares everything. I think that's probably everything that's really we need here at the moment. Now, Nordita typically has 2 types of postdoc opportunities. Nordita Fellows, so Nordita typically has their own funding for employing postdocs, and then people in Nordita, if they grants, of course, can employ postdocs on these particular grants. At the moment, there are no open positions, but what the information that was public on the website was saying is that this may resume for the 2026. So sometimes in 2025 makes sense to check and see if these schemes have resumed. There are other funding opportunities. So Werner Grant Foundation, so we have Robert here that have funding from them. So in case there are success stories, so people manage to get this funding, and yeah, in case perhaps we can ask you for your experience, how that works. So there are 3 types of funding that I would like to highlight from them. Now, for navigating the website of the Van Grant Foundation, don't be fooled that it has a little British flag. There is very minimal information in English, so Google Translate will be your best friend. Swedish has very regular grammar, so I think it's translated usually really, really well. At least I thought I could understand everything through that means. So, yeah. So first, outgoing fellowship. So if you get interested and come here for a PhD, then you will be eligible for this outgoing fellowship. So if essentially if you did PhD in Sweden, and this is for junior postdoc, so 3 years from PhD, you can apply for a fellowship to go for 3 years somewhere abroad. And then you have an exclusive kind of opportunity to apply for additional 2 years, so-called return phase at some Swedish institution. So the foundation covers salary. The amount depends on the country you're in. I mean, just how much funding you need. Maybe they adjust it to somehow typical local salaries. And the website mentions a startup grant. This is, I believe, total for the whole duration of this fellowship. This is 400,000 krona. And the deadlines are typically each year, 31st of January. Then the incoming fellowship. So this is for people that are currently not in Sweden or have not. Okay, I'll explain this requirement in a moment. So this is the moment I have to take the bull by the horn. So you cannot be longer than 9 months in Sweden at the deadline of the call you're applying to. And the easy thing is deadlines again on each year, the 1st of October. So if you've only recently come to Sweden and you're looking to extend your position, or you're maybe, or if you are outside of Sweden, obviously that doesn't bother you. But that's, So the point, the goal for this is to bring people from outside, so the duration of this funding is between 3 and 24 months, so up to 2 years. And this is not a salary; it's a fellowship, but it's tax-free. So this is a fixed amount you get. And the website mentions maybe that's where maybe there is some particular Swedish expression, but the way I interpreted it is that it doesn't have a fixed travel budget, but there is if you have an actual travel related with your research, you can get that reimbursed. Now, the important thing that applications are actually submitted by the host in Sweden. So it's not the person coming that is applying. Of course, person coming probably will be the one looking closely at this call and looking for some local contact and making sure they are interested and that they will participate in preparing the application. And in the end, it's the local host that actually has to do all the clicking and filling of all the boxes. But that can be easily arranged, so people can prepare everything that's needed. The proposal is again quite minimal, a couple of pages, and then there are some CV, publication lists, and so on. So that's essentially something that really has to be done in some prior contact. So that's something one essentially cannot arrange at the last minute just before the deadline, typically, because somebody will need to submit it for you if you are interested in coming here. And then visiting researchers. That's, I guess it might be seen as a scheme for people here in Sweden to invite collaborators from abroad. But also if you would like to come and you have a good colleague that is willing to put some application like this with you, that could be an opportunity to come for 1 to 12 months. And again, it's not a salary, it's not a position, but it's essentially if you have some longer term position elsewhere, but are interested in coming and work for some time in Stockholm, that this could be a good option. Again, this is for, so this particular, this last scheme is for more senior people, so 5 years, you have to be at least 5 years post a PhD. And yeah, the money is supposed to cover the additional expenses because you are not at your home institution. And the deadline is twice per year, so 10th of March, 1st of October. Yeah, perhaps could be an interesting opportunity. And then there is, of course, a Swedish Research Council. I think every country that probably has PhD studies in physics would have a research council, and the same, of course, is in Sweden. And they also have a number of different funding, but I think only two are really directly relevant to the goal of this talk, that is more oriented at people at PhD or maybe just finishing PhD studies. So there are international postdoc positions, so that's for people that I would make decision to come to do PhD in Sweden, and then we'll be looking what are their options after that, if Sweden can support their further career even outside, and the answer is yes. So there are these international postdoc grants. So they are again for junior people, quite junior actually. So 2 years from PhD, you can apply. You can apply within 2 years. The duration is 18 to 36 months. I have here the grant amount per year. So this is based on the last call. So perhaps they be adjusted. The deadline is typically January, February. I think it's already the deadlines are actually given already this year. I think it's something around 20 February where it's a closing date. And so even though this is an international postdoc, the information stated is that you need to submit it with a Swedish administering organization. Perhaps there is someone here that could say a few words about like what's the logic. My understanding is there's no return phase, so essentially you want to do a postdoc abroad, and you need to find a Swedish administering organization, and that just doesn't seem very clear. Maybe there's someone that can complement, give some. Do you know anything about this?
Not much.
Okay, yeah. Well, I guess in case one has to go. Well, VR is it usually the abbreviation for this is because it's Vetenskapsrådet, VR. Yeah, perhaps there is some more detailed information on this contact where you can shoot an email to understand what the role of this organization should be in this whole endeavor. And then there are starting grants. So if you know about the European, the ERC Council starting grants, that's a little similar. So this is for researchers between 2 and 7 years past PhD. They are 4 years in duration. There is ample research budget per year, and deadlines are typically March, April. Again, so here you apply with the Swedish administering organization, but in this case, this research is supposed to take place at the Swedish organization, so that's of course clear. You need to find a host university, so that's again something one needs to arrange very early in advance, so that it's clear that the university you would like to go to can support your application, and often also universities offer some additional benefits if you get such grant. These are quite attractive for universities. I believe some universities may offer even tenure for VR starting grants. Not anymore?
Not for VR.
Not for VR, okay. For the ERC ones?
Voluntary.
For voluntary, okay. Yeah.
For ERC, maybe if you negotiate beforehand or afterwards.
Oh, so all the more contact beforehand and get some course on negotiations. I think that's everything I collected. In case slides will be available, I've included a link to the RQI Circuit page where you can find all the links and summary information and perhaps any complement information that we'll gather. I guess I'll just close wishing everyone success in any applications I'll be preparing. Of course, if you are interested in any of these local opportunities, I'll be happy to be a point of contact and help you find other people you might want to connect to. So yeah, I guess it would be easy to find my contact details. I wanted to put something a bit festive because it's the end of this wonderful workshop. So again, I think really many thanks are in order to the organizers, Evan, Rick, Vasileios, and Germain. They did all the work, and of course it was really quite a bit to get it running, and they are all really quite fresh here as well. So I think yeah, really we all really appreciate your effort. And so for this festive atmosphere, I thought to ask what the AI would imagine as composite quantum snowflakes over Stockholm, and that's what it is. So yeah, I think we are through.
Do you guys want to do some final words? I want to definitely say
sorry, okay.
Evan, do you want to say something, or any of the local organizers first? Definitely. You don't have to worry too much about the schedule.
No, I just want to put something up on the back.
No worries.
Okay, thank you everyone for coming. I'd like to thank everyone here, the audience, the speakers, for taking time to come out at such a late time now in Stockholm. I'd like to thank everyone online for joining us through YouTube. I'd like to thank Magdalena again for the wonderful career development talk, and also personally for hosting my stay here in Stockholm University for 4 months. I'd like to thank the co-organizers Germain and Vasileios for helping me, particularly regarding catering on the day. And thank you, Rick, for your job organizing all of this week out, every week. Yes, thank you once again.
All right, perfect. All right, and then the final things. Again, thanks everyone. Thank you all of the speakers. I really enjoyed the talks today. Made the day feel a little bit shorter, although it was fairly long. Magdalena, thank you so much for the career development talk and for everything. Also for the discussions throughout the week. Robert is not here anymore, but thank Robert for the accommodation. Thank you. The local organizers, the guys did an amazing job. It's amazing how actually the circuit can work with like a couple PhD students, putting some effort, talking to everyone, collecting the abstracts and making this work. It's everything on them, it's not on me. And finally, if you're still with us watching online, probably you will like to join next week, the RQI Circuit in Bremen, starting at 1 p.m. Central European Time, November 24th. So thank you so much, and yeah, see you next week.